Testing 1, 2, 3. Okay, that is working. Let's put the graphics on the screen. Boom. Boom. Okay. All right. Let's try this. There's a Poleville.c, which is for Polish evaluation, forward Polish notation. Okay, it's 43 lines. Wow, okay. Polish evaluation is very short. Depending on available equipment features, the user may wish to rewrite the program in microcode or assembly language. We're not doing that today, but we could think about it later. Okay, wait. Okay. Answer equals answer times x plus coefficients of cursor. Cursor plus equals 1. I minus equals 1. I mean, I is just counting how many steps. So really we want for 1 to n. Right? right? I mean, let's make this as simple as it is. And then, right? And this is just that. Which means we get, really? That's what this function is? Okay, let's go back to the original one again. Okay, this is what their frickin' code looked like. No indentation at all. Which, okay, some of this is just having to compile in C. But like, as far as I know, this is what this function is. I'll put the return value. Right, because I isn't used for anything. P just goes forward and reads items. For the polynomial, the 0th term isn't right, but that's like here that's here and here that's here, right? Unless I misunderstand what you're saying. Evaluate polynomial when coefficient of x is 1.0. Oh, of x to the n. Otherwise, same as po level. Let's just do it and see if it comes out the same. I'm just going to not look at what's above, and I'm just going to redo this. So P1 eval. Okay. Ands. X plus coif sub cursor. Cursor plus equals 1. That's sort of what the star P plus. Okay. Oh, we're going n minus 1 now. Okay, while true, we do this thing. We say I minus equals 1, if not I break. And then return ands, all right? So I, again, is just being used to count from n minus 1 down to 0. This is coef cursor plus equals 1, right? Okay. So let's again do this. So it's coefficient 0 here, obviously. So that makes cursor 1. So this is for actually, I might have got, hold on. I is n minus 1. Okay, I think I got this actually this wrong. I think this maybe should be 0 to n. No, not 0 to n. Hold on. So this starts at n minus 1, and goes down to 0. And it, oh wait, no, never mind. 0 isn't, okay. If it's 1 at the start of the loop, then it breaks at the end of the loop. So it doesn't do an iteration for 0. Okay. So this does n minus 1. This goes from 1 to n minus 1. Right? And then I doesn't do anything. And then again, so cursor also just goes from 1 to n minus 1 as well. So this is again just this, and then we don't need this, and we don't need that. And there. So like, that's what I get for this as well, right? So this is 1 to n minus 1, and we're just adding x. That's the only difference. Well, x and then not doing this. You need to use Horner's method for polynomial. Look, dude, I'm just transcribing the code, okay? I don't know what the Horner rule is. I just work here. I don't like this 6. Was this originally in Fortran or something? Like, look at these function names, man. I'm going to rename it. I'm going to rechristen this polynomial eval. Okay. Hope I didn't screw that up. So n for this is around 4 or 5. I guess that's how many terms are in the approximation. We're doing the tangent function right now, by the way. So, you know, that's not that much. We could, if we wanted to, inline these and make them. I'm not going to do this right now, but if you wanted all these functions to be fast, you could say this, right? And then it knows exactly how long the loop is. And then hopefully the back end automatically optimizes that. But we could even do this in the front end of just like crank this out. Like that would be kind of fun, actually. Like have an automatic unroll. Like you know how HLSL has like that? We could do that. Anyway, we're not going to do that for now, but it's just, this is exactly the kind of function that this programming language like wants to help you crank at. Won't changing the iteration order of the loop change the result of ands? We didn't change the iteration order of the loop. Okay. The reason we didn't is that we were always, so in the original code, let's look at it. Let's pull it up if you can even read it. So in the original code, this P is the coefficients that we're reading. We assign P to this array coef, and we just go star P++. So this is going forward the whole time. This I is just used to know when to stop. It's not used for anything else. So you can reverse I, it's fine. And then once you reverse I, it's actually the same as this index. Do you see what I'm saying? Don't forget to remove the inline. Yeah, okay. Okay. Speed idea. We can mark polynomial star as inline and also make n a compile time constant and have some nice inlines guaranteed loop unroll action. Okay. I mean, I might have, it's not to say that I didn't screw something up. Oh, double polyval. I left this pasted in here. Okay. Return ends. Because I forgot this part. Okay, argument 2 of polynomial eval. Oh, right, these aren't float 64s. These are S16s. Which then, okay. Do we do add int? We don't. So we have to cast this. We're being explicit about the cast. More bits. Okay. I have an idea. Yeah, this I want to simplify anyway, but let's figure out what this constant is. What does more bits look? Come on, bro. More bits. atan.c, asine.c. More bits. If dec, like it scares me a little bit that these constants are very different, but okay. All right. More bits. Colon, that. Okay. Really? Do we not correctly parse floats with E in them? We actually might not. We might have to put this into the compiler now. I honestly don't remember if we do this. Okay, we do. Just no uppercase. Let me test this. Well, I mean, that probably, for the way that we print floats by default, that's probably right. Like, that's a very small number, and the default print doesn't actually print in scientific notation. Maybe we should do that at some point. Let me just make sure it's not 0. Yeah. So it's probably right. Oh, let's more bits times 1e17. 1.0e17, right? Whoops, wrong program. Wrong program. E-O. I make you say E plus 17. Interesting. All right. So when we multiply back 1e17, we get 6.123234. Yeah, to the number of digits. Okay, so it seems to be working. Seems to be working. Okay. This also means we compile the game. Let's see if the game completely explodes, because it might, because we replaced tangent and atan2, or we replaced atan and atan2, And that means our perspective projection might not work anymore. But it seems to work. I don't know. I mean, I don't know exactly. Like, it's used in various spots. Let's just make a little test. Just make a little test. For, let's say, samples per circle is 10, 11. We'll make it a weird odd number. Actually, no, let's just do this. Let's say degrees per iteration is, or radians. Radians of the lost arc is tau divided by 11.3, I don't know, right? Theta 0 is minus 7, right? 7.0. While theta 0 is less than 7.0. Oh. So theta is theta 0. Theta plus equals radians per iteration. Okay, but okay, CT is cosine theta. This is still using libc. ST is sine theta. All right. T is ST over CT, right? Tangent is sine divided by cosine. Am I remembering that correctly? Okay. So A1 is A tan of T. A2 is A tan of ST CT, right? A tan 2. No, so early on I had to decide what types implicitly convert and what don't. And so I made this rule where, okay, look, int does not implicitly convert to float, right? So if you pass an int to a function, that will not convert to float. Except I noticed that a lot of the time you just want to multiply an int by a float, right? And if you multiply an int by a float, it's very clear that you meant to do that probably because, you know, that just seems very clear. So I made an exception for int times float, but I didn't do it for int plus float. We might change that. We might say int plus float is okay, but we haven't yet. And honestly, it doesn't come up that often. Like int plus float is not a common operation. Any reason why I put the type in arguments to print C style? What? When? When did I do that? It is inconsistent. Yeah, but the best solutions sometimes have inconsistency. I don't know. I mean, I'm not that worried about it. Like changing that one either way, I don't care that much. It's like not super high on my list. Did you see that wrong? Like where? In the little test that we did? That we deleted, I guess? %G is not a thing. %G, that does not how this print function works. All right, so we're going to print theta is whatever, A1 is whatever, A2 is whatever, and they should all pretty much match. Let's see. except that I broke it. How did I break this? Like what? Maybe I screwed up ATAN or something. Like, come on, bro. All right, well, let's see what's happening. Watch it be something super dumb. Stack ATAN. ATAN is recursing infinitely. See, I'm supposed to be casting up to float 64, and I was stupid and I typed 32. So that function just is, okay. Wait, where? Oh, because we're returning. We have to cast down on the return. Okay, I see what I did. This was right. This one was wrong. All right. Okay. Okay, well, yeah, these look approximately right. The thing is, once we get past a certain point, let's wrap theta for printing, because we're going to get back an angle between minus 2 pi and 2 pi, right? So th is theta while th is greater than tau times 0.5, th minus equals tau, while th is less than minus tau times 0.5, th plus equals tau, and we're just going to print th. So we're just wrapping the angle. We could do something with like a semicolon. Oh, because that's a call. Oh, weird. All right. Okay, so now they pretty much match. I mean, there's numerical error, which we expect. ATAN and ATAN2 are always returning the same thing, which you would expect because they call the same code, except right here. What up with this? Okay, we actually have a wait. This is 3.14 apart. So wait, do we have a weird domain thing? It's kind of cool when you can do var name, not when you want to localize. It's not cool. Not when you want to refactor your program and change the name of a variable and half your strings are like in frickin' data files that you forgot was an issue. Because it has more information, it can output all 4 quadrants. ATAN2 has a larger range than ATAN. Let me think about this. I mean, we were just looking at the source code, right? And ATAN2, in this implementation, actually calls ATAN. Here, like all of this is just handling edge cases, right? And it's weird because I thought there would be epsilons or something, but it's literally handling 0. So anything that is not exactly 0 goes through the main path. Anyway, almost this entire function is zeros, infinities, and nans. And then we take the atan. Right, okay, and then we do this stuff, right? So if code is equal to 2, we add pi. If code is equal to 3, we subtract pi. So that's what quadrant are we in. Now this code stuff seems really dumb. I mean, let's not say really dumb. Let's just say it actually seems more complicated than we need, because we only set code equals 2 here when x is less than 0, and like just put x is less than 0 here, right? And just x is less than 0 here. You're only going to do one compare anyway, and you're not going to need this extra variable. So this is weird. It's on my list to simplify this. We might do it now. Oh, but it's okay. That's if x is less than 0 and y is not less than 0, right? That's the problem, is it's equals. It's equals, but this isn't. This can just be x is less than 0. I don't know. This integer code thing, I don't think it's necessary. All right. Can someone who's mathematically literate explain what epsilon is? So in math, epsilon means smallest value. In like numerical computing, it doesn't quite mean that. In numerical computing, it means a number small enough that we don't really care about accuracy less than that. But it doesn't mean the smallest representable number. It just means pretty small. Why not make those codes some enumeration? Yeah, maybe. I mean, the question for me is, as we port more functions, is this going to happen a lot, or is this just right here? You know? Not sure. Shouldn't I be moving by tau? I am moving by tau. This tau times 0.5 is the range that we're checking. We're going between positive half a circle and negative half a circle, right? That's all. If you could give LLVM 24 hours to optimize your code, could it go faster than a release build? Probably not by much. Not currently, but people are always working on compilers. Okay, so I believe that we have succeeded at getting rid of another. I'll show you guys what I was working on, right? Yesterday and this morning, we were doing removal of libc dependencies for some functions. And somebody asked, what else do you depend on? And I was like, math. And then I was like, oh yeah, we were in progress of backporting of doing some math stuff. So why don't I do a little bit more today and just make progress on it? So we did that. So atan and atan2 for both float 64 and float 32 were in here, which are all declared as being in libc, right? And so we don't do atan anymore. Here's a question, everybody. To do cosine and sine and presumably tangent, should I try to just do that purely with machine instructions, or should I port stuff from this library? I want to do at least one more function. And cosine and sine are basically the same function, so, you know, it is what it is. Like, x86 sin cos are slow and inaccurate. Are there not, like, I don't know AVX at all, or at later SSE. Is there no AVX or SSE sin, sine, or cosine? Maybe there aren't. Maybe there aren't. Okay. It's in separate instruction sets. What separate instruction sets? All right, well, let's take a look at let's take a look at me learning how to drink water so I don't cough. Do I have an opinion on model formats? No, I don't. There are AVX ways to do sine and cosine faster. Yeah, I mean, now I'm thinking, though, we don't want to require AVX. I mean, we do sort of require 64-bit CPU, but again, we're going to go to ARM. Let's take a look at what sine and cosine look like. They're probably simpler than tangent, right? How could they not be simpler than tangent? So, whoa, there's some numbers. Sine table. So are the sine and cosine, do these just call sin cos, or are these separate? They have a separate, oh my God, this looks terrible. Well, it'll be a very small amount of code once we, wait, I thought the whole deal was sin cos. Okay, first of all, why are they just not making sine be cosine of x plus pi over 4 or whatever it is? That's kind of whack. I mean, I guess they don't care about code size, but I care probably a little more. Sin cos are from the old 10-byte float instructions. I figured that would still be true in software, though. Maybe it's not. Let's take a look at sin cos really fast. Since range reduction is time consuming, the reduction of x, range reduction is time consuming, all right. Okay, so this is probably a big file because it's like, hey, there's a lot of things you could do. We could actually, instead of this being compile time options, we could make this a polymorphic argument like, how accurate do you want your sine? Six megahertz IBM AT clone and Microsoft C version 4. No wonder range reduction. This is expensive. SSE trig functions here. Do I care if different architectures give different answers? No. Within reason, of course. Okay. Table of sine from 0 to 90. All right. Wait, is this in degrees? This is literally, the argument is in degrees. That's kind of crazy. Although, honestly, I'm not sure why we use radians for everything, if I'm being honest. Doesn't look like there's a sine cosine instruction in SSE. All right, so this is what sin cos looks like. It is 358 lines. I'm not crazy about that. It'll get shorter if we port it. A lot of that is a table, though. The table will not get shorter meaningfully. I mean, you can put numbers on the same line. Okay, sine is 300 lines and doesn't use the same table. Oh, this has cosine and sine. So this is like a different implementation. Okay, so first let's look at, like, why do they have a different number of trials for sine than cosine? Like, what? This is a very strange methodology. 17,000, but I don't know. Okay, this, sometimes I just look at these very organized comments with pertinent information and I'm like, all right, whoever did this was really on the ball. And then I notice things like that and I'm like, wait, what? And then why is sin cos a completely different implementation? Okay, this is very old, I guess. This is probably actually from 1987. This is at least updated in 2000, right? So, like, I guess we use this one. He's no longer at 30 Frost Street in 2000. Like, I think it's hilarious that in 1987, people thought it was useful to put their street address in comments. Like, write me a letter. I don't have email. Okay. So these are much smaller tables. And I sort of feel like the smaller tables are going to be better on modern CPUs. Because you like don't want to spend a bunch of cache. This is 92 times 8. That's, you know, almost 1K. That's not that bad. A 1K table. I don't know. Sign vanishes as its argument vanishes, so being accurate around 0 is different, but still easy to do. Let's just look at what this looks like once we start digesting this. All right, so I'm just going to paste this into our file, not this file, and we're just going to see what it starts looking like. And we're going to put it, like, I think people feel like sine and cosine are more major than ATAN, so they're going to go up here. And we're going to start just by figuring out which tables to use. Like, this is what I want comments on, is like, why are these coefficients different? So am I unknown? I'm not DEC. Okay, am I IBM PC? Like, maybe. Like, this is number 16-bit short. I mean, we did a 16-bit short for tangent and it seemed fine. So my guess would be this is probably lower performance. Except maybe it's not because, oh, I don't know. Okay, let's delete DEC. We're not DEC. This computer is not made by Digital Equipment Corporation. So, or do I do MIEEE because we have IEEE floats? The numbers are kind of different, although, wait, that's that. Oh, they're in opposite order? Okay, wait. Are these actually float 64s in reversed? No, they're not reversed byte order. They're just reversed short order. I don't understand. This is where you should have a comment. This is like, okay, this comment is fine. But like this, like what is it, man? It's a polynomial. We know that it's a polynomial. That is a thing. And that said, like, we actually, for our ATAN test, we actually should call libc ATAN as well. Rather than just comparing these against theta. Because I might have picked the wrong table and it might do something really wrong. I don't know. I mean, I'm guessing MIEEE. I don't frickin' know. We need to find, maybe there's a header file that explains. what to do. Is there a global, is there a README that says, here's what you define and why? README. Check the files mconf.h and const.c. mconf.h. The symbol for IBM PC should be defined. Oh, big endian IEEE format is MIEEE. But why are the numbers different? Like, we don't... I need to go back and look at the code to make sure it's not spam somehow. Like, we don't cast these to float in a naive way. Well, okay, these might go to a totally different function, okay? But what I'm thinking about actually is when we went back and did this, we have similar things. P and Q here, right? Boom, 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 boom. I should go back and double check which one of these I used. But we passed these to polynomial eval and we just cast them. Oh, dude, I think I did this wrong. I think it's, okay, hold on. Hold the horses. Hold the horses. We need to comment this stuff out. Like I don't understand why he is doing the numbers, maybe in 1987, or doing the integer versions, I mean. Maybe like in 1987, that was a good idea, and he just kept doing it that way. Okay, so this is all commented out. Do we still compile? Yeah. Okay. This P and Q came from atan.c. I picked MIEEE, okay, which we've established is wrong because it just sounded good. So we want IBM PC, but why don't we just do the unknown? Like, this just seems like what we should do. Okay, so let me double check. I think I know what I did wrong. Here, like, it's relying on C not type checking this, on like KNRC, because it's passing this array of S16s, and then we're treating it as array of doubles. I did not do that because I saw the compile error when we did type check it, and I said, oh, the argument is wrong. Argument is not wrong. Okay. So I don't understand why he doesn't want to just write arrays of doubles. And he didn't explain that as far as I've seen. Let's see. Because I would rather just put the arrays of doubles. This is the wrong README. Oh yeah, mconf. Accommodate other types of computer arithmetic. All constants are also provided in a normal decimal radix, which one can hope to correctly provide a suitable format by the available C language. What do you mean a suitable format? Like, you mean how they live in memory? What? Is a predefined set of machine arithmetic constants for each. The numbers mac, hep, max, num. Several parameters are preset by the configuration symbol. Okay. I literally don't understand why he is doing this at all. At all. It doesn't make... Given that float-based conversion code has been notoriously bad and inaccurate in the past, you're assuming compilers are not any better. Could be. Could be that your C compiler would not give you the right number in response to a lot of these things. I'm going to go with that. Although, again, like there's funny ways how it's just very easy to not say in comments the thing that people really want to know. It's a fine art to like figure out what are people really going to want to know. All right, well, this is wrong, clearly. So our approximations are wrong. You know, I was looking at this and I was like, these are pretty far, actually. But maybe it's numerical error from going forward and back. No, that's too much. So our approximation just sucks because these are completely wrong. In fact, I'm amazed that it's not a completely random number. Like, I don't... Okay, whatever. Let's go for the Unc. We're going for Unc, the man from Uncle. All right. So Q, I guess, is always used for the implicit one function. All right. All right. Okay. P and Q. And then our polyvowels. Okay, now it's making, whoops, now it's making more sense. Somehow the game ran with our bad approximations. All right, let's see what happens here. Oh God. Let's change the compiler. I was deciding to be pedantic and require a plus. Let's not do that. It's just fun to be able to change your compiler. Floating point constants that use E do not need to put plus for positive exponents. Maybe I should do capital E also. You know what? We're going to do our... Are we translating this into a buffer? By plus or minus or a numerical digit. Okay. Okay, let's rearrange this. If C is equal to plus, or C is equal to minus. Right? So we're actually just transcribing this into another buffer that we passed to scanf or whatever, I think, which is really goofy, and we should change that. Else if is digit C okay. And then we're going to do our stupid, hilarious thing that we saw from that other code. All right. Yeah, this is not for integers. This is specifically for floats. All right? Like, we start out parsing integers, right? OX handling is like up here, OB, OH. And then based on what we see, we do this. If we ever see a decimal, you know, then we start parsing float by using A to F, because we sort of just copy it into another buffer and then punt, which is fine for now. I mean, later we could do something else. Okay, so problem is that base conversion sounds easy, so it's easy to write code that mostly works, but you have to compute with extra precision. Then the output to be able to produce every possible float representation. If you're writing float routines that guarantee some accuracy, you actually care about that. But those integer tables didn't have more precision. Those integer tables were just you know, 64 bits as well. Now, you mean the compiler's base conversion routine? Right, yes. Yes, I understand what you're saying there. We just did, we literally just did string to float yesterday and the day before. We were porting a routine for that. And so, yeah. Really, the slick thing to do would be to use hex floats anyway, in this case, because then there's no uncertainty about that whatsoever. I kind of want to do that. Let's see if I didn't screw up the Lexer. Whoops, I didn't change that. That is an incorrect error message because we didn't actually say that. What is going on with my compiler, guys? All right. So we changed that one and we didn't change this one. Okay. So first let's Okay, this is much closer. This is tremendously closer. Okay. I feel a lot better about this. Remember? So like these are the current numbers. They're sometimes matching to as many digits as we're printing, right? Before it like wasn't really that close. It was like, eh. All right. Crisis averted. Now, let's actually, I want to figure out the hex floats for these things and see if they're off or not. They shouldn't be off. But like, I'm going to go here and I'm going to say P cast a pointer to U64 p.data, right? And then X is dereference P and print whatever format int X base equals 16, right? Okay, so this tells us what this number is, this first number in P. And we can go compare that with what was in the ATAN file, all right, under some of these other things and look at the byte order and stuff. So IBM PC, right, BFEC, 007F, A1F7, 2594. So it is exactly the right bits. But if we want to be very picky, we could do the following. For all these numbers, right? We could say, instead of this, we could say 0H that, and maybe put the number in a comment. And this sort of tells you we care about every bit of this number, although I guess that kind of does too, right? Anyway. The fact that it was even somewhat close is amazing. I know. I don't understand how it was that close. I'm sure if I knew the math better, I might have some idea, but like, I mean, it was the wrong endian. Like, that was crazy. It was the wrong endian and it was still kind of there. You heard an idea that most physics engines can never be deterministic, even for two machines of the same platform, because of more than just floating point accuracy. Any idea why? If they're multi-threaded, they won't be deterministic. That's the main reason that I can think of that's legitimate. So I'm kind of up in the air about which of these I want to do. I think I'm going to do the hex floats. They're shorter, they're faster to parse. Are there some that are still far off in the middle? No, like if you these are just reporting in different quadrants. Okay, if you take the difference between these, it's 3.14159, etc. It's pi, which is fine. Okay. So, what about CPU state and speculative execution? Could that affect determinism? It shouldn't unless there are bugs in the program or it does something really stupid. Okay, so we're going to do this, and I'm going to go for P whoops. So we're just going to print out the thing. Okay, these are our hex floats. Wait, they're all C0 whatever. Really? Really? Let's go to here. So actually, let me just output. This is goofy, but I guess the C0, this is all like exponent stuff, so that makes sense. These are all close to 1 or close to -1. All right, let's go all the way. We're going to go in style. Oh, no, we don't our print function doesn't print doubles out to full. Never mind. We should do that at some point. Like, why are you putting E1 on there? I guess just for consistency with other parts in the program. All right, so that's P. And then we're going to do Q. All right. Did I screw it up by pasting in P? No, it still looks fine. Still looks fine. Okay. Q is these ting-tanglers. See, I like this part. Like, assuming we have the correct understanding, like, oh, the float parsers were bad on some systems and whatever. It's like, okay, we really can make the code simpler and more robust by factoring away some of that stuff that is historical at this point, right? And that in this language never will be a problem. We always will have hex floats, for example. Oh, I need to put 0h here. All right. So float parsing will not ever cause a problem here, which is great. Why didn't I get an error? Maybe I did. I didn't see it. Oh, no, because this doesn't... No, it does use that. I don't know why we didn't get an error. Maybe I didn't save the file. Oh, I didn't save the file. Yeah. Look at reference constants from that file for IBM. Oh, to make sure they match? Yeah. They should all match. Good reason to double check, though. Okay, IBM. Or actually, the MIEEE will be in the same order. Even though this is the right byte order, if we read it out, it's going to be this, right? BFEC, 007F, A1F7, 2594. I could have put little underscores here. I don't know if I care. CO30, I'm going to go 4 at a time. CO30, CO52, CO5E, CO50, 7F, 2854, CO8C, BAP. I mean, it's all matching. The miracle of computers is that when you get it right, you know, sometimes. Okay. Q. I mean, yeah. Very good. What does this look like if I do underscores? Do I like this? I mean, it's more readable, but who cares? Is sort of how I feel about that. Yeah. Nobody will read them. It's a good point. It's a good point. Let's get rid of these. Okay. Okay, now we can go back to sine cosine. And we're going to go UNC. We have decided that UNC is the way to go. We can do our conversion on these again later, but for now, we'll just leave them. It's weird indentation, but okay. DP1, DP2, DP3. We'll see what these are. No IBM PC, no MIEEE, no ANSI prototypes. All right, great. We're actually, you know, the code for this, it's not as much code as I feared it would be, especially once you start cleaning all this stuff up. Like, all right. So like all these variables we'll take care of. We are doing all the -0 stuff, right? All right. Math error. Do we have a nan? Yeah. So we can return, wait, we don't have a float 64 nan. Why didn't we define float 64 nan? What is float 64 nan, everybody? I'm sure it's all F's out here. What is this part? I guess it's the entire, I don't know. Let me try this. This is kind of stupid, but F is float 32 nan. G is cast float 64F. I don't know what we print for that. And then oh, geez. Come on, guys. Okay. That's a bad error message. We have to put that in the, it's putting the wrong type. Okay. Seven F E0. What? That's not right. So casting from float 32 nan. Oh, maybe there's a lot of nans, right? Nans are determined by the exponent only. Is that right? I don't remember right now. I think just 7F, all Fs would be nan, right? Let's see. Yeah. So we're going to say float 64 nan is that. That's our theory. Casting nan truncates. Interesting. Just copy the infinity and flip all but top mantissa bit. Wait, what? Really? I got to remember my IEEE. So you're saying nan would be OH, OOO, and then a bunch of Fs, right? Hold on. Not sure about that. No. I might have misunderstood. 7FF7. Nan has non-zero mantissa. Okay. Wait, why is this 7? Why is it not? Why are we not setting the top mantissa bit? Only special bit is top mantissa bit, which is signaling nan. But it was also nan when I set it, right? If I set this to F instead of 7, it still claims it's nan. Wait, there's 53-bit mantissa, right? How many? 4, 8, 12, 16, 20, 24, 28, 32. 36, 40, 44, 48, 52. Top mantissa bit would be this one. So what? Oh, 53 includes implicit bit, right. Okay, so it's bit 52 is clear. Okay. Okay. You can see I need to do this more often. It's been a long time. I like IEEE 752 floating point number. Like they're cool, you know. They're one of the things where once you know basically how they work, like before you know how they work, you're just like, floating point numbers are weird, not accurate things that I don't understand. But once you get them, you're like, oh, this is like a thing. Seven FFF01 is NAND, but 7F all 0 is infinity. I see. Right. So actually, any one bit anywhere in here is going to be okay. A quiet NAND is represented by any bit pattern. Okay, so that the top bit means quiet NAND. I never got into signaling versus quiet NAND very much. NAND payloads have always just been an underused debugging feature. That is true. I have not used them. So, all right. So we have a float 64 NAND. Ain't no party like my Nana's tea party. Hey, ho. All right. Sign. If it's not finite, I don't know what we do here for an error. Do we signal errors? I kind of maybe think it might be a nice convention to have like an error log, but that's not ever meant for the user. Like this is just the error log for programmers. And routines like this that are in a library could log to that, and it would be turned off for release builds, right? But then you wouldn't have all these weird, like silent failures, right? Like logging is a really good way to say something's wrong, and here's some information about it. Did Steve tell you that perchance? Steve. Okay. If x is less than 0, this is just like what was in tangent. All right. So we're just going to comment these out for now. I don't remember what lost is. That must be defined in the header file. Why is it a static? Like, why is that a software changeable number? I don't get it. Oh. Okay, J sign. All right. Oh, that's a, wait. That's seriously an integer. This is an implicit cast. Like, seriously? What? Okay, I see. This is not an angle. This is... All right. Map zeros to origin. We'll leave that for self-documenting. Why did you put 07? Octal 7 is the same as 7. Is the same as hex 7. Like, all right. Well, I guess you're sort of saying it's an octant. I have no idea what this code is doing at this point. We're going to have to comment it more thoroughly. So J is, so it's 8 is 360 degrees. So yeah, each integer is 45 degrees. Right. Ain't no party like my nana's tea party. All right. That's z squared. If j is equal to 1 or j is equal to 2, else wait, why aren't you using ZZ in here? He's doing Z times Z times Z. He already has ZZ, which is Z times Z. From here. I don't get it. All right. Okay. Ain't no party like my nana's tea party. That's much shorter, but it calls double underscore sign. Yeah, that's not good. The best part is that the comment says ZZ. So why Why would the comment say ZZ? Is he worried about like, okay, here's my theory. He's worried about having too many numbers to get pushed and popped on the x86 floating point stack. Remember how, or the x87 floating point coprocessor was stack based or something? Like, I don't, but then he uses it in the call to PoLev 1, so. You think J is guaranteed to be even? That is true. J is guaranteed to be even. In fact, so it's even and it's not greater than 3. So it's 0 or 2. Wait, then how is it 1? Do you guys want to explain to me how it's possible for J to be 1? I think this was somebody's oversight and they didn't realize that this was not possible. Let me double check that I didn't like goof this really bad, but I don't think I did. If J and 1, J plus equals 1, Y plus equals 1.0. And by 7, which is not going to make an even number odd. Subtract 4, which is not going to make an even number odd. It can't be odd, guys. Oh. No. If J n equals 7, then J equals 4, which is greater than 3. So you subtract 4, you get 0. Yeah, you can't. Look, if it's even, modulo will not make it odd because it's modulo by an even number. It's mod 8. Subtracting an even number from an even number makes another even number. It doesn't matter what it is. So I swear J is 0 or 2 only. Nobody sees a problem with this? Okay, so we're going to put a no check in here and say, okay, we can submit a patch request to this guy. He hasn't heard from anyone since the year 2000. J cannot be negative, I don't think. I mean, certainly here, anding by 7 will give you a positive number. First it's even, then it's positive, then it's not greater than 3. So it's 0 or 2, guys. I played a lot of Everyday Genius Square Logic. I know how to do this. It should be 0 or 3. How are you getting, 0, 3, or 4, or 7 after the and? I thought you were saying end. Okay, wait. So here, it's an even number. I don't even know if this... I don't know what the potential range is, right? Like x is an angle in some range. Maybe it's already normalized to minus pi to pi. I don't know, right? And I don't know what this does. But the point being, we cast the integer. Anyway. Could probably also be jn2 instead of j minus equals 4. Yeah. But that, I'm not sure that matters. I'm not sure that helps anybody. Multiplies a floating point value x by the number 2 raised to the x power. Okay. So that's divide by 16. I sure hope this is faster than multiplying by 1 over 16.0. Like, how could it possibly be? We're going to have to look at that. Or is it, wait. Load S just offsets the exponent. I see. That's actually going to be slower on a modern CPU. Well, except you don't, right, you don't change the bits, I guess is the point, right? You don't change the mantissa bits at all through numerical error. But that won't happen by multiplying by 1/16 either. Because 1/16 is going to be exactly representable. fpmul instruction probably isn't going to have a fast path for that. Yeah, but the thing is, well, I don't know. Are there like loadx machine instructions? I'm not aware of any, but I'm not super up on this. The thing is, like taking a number out of a floating point register into an integer register, modifying the exponent, and then putting it back in a float register is probably slower than a float multiply now. Like float multiplies are fast. But I'm not completely sure about that. If you're good, it can be done with 5 integer operations. Well, I mean, somehow move float, like moving between float and integer registers is not cheap. That's just a thing that like hoses pipelines a little bit, or at least it used to. I don't know about now. Like you used to not even be able to do it. You used to have to go from memory. So like you load the thing. Okay, you put 4 in a register. You left shift it by whatever. You move float to int register. You OR them. You move into, or not OR, you add them and hope you don't overflow, right? And then you move, which I guess you're guaranteed not to due to the angle range here. Yeah, so it's like, it's 5 instructions if you can go int to float and float to int in one instruction. And even if you can do it in one instruction, is that one cycle? Questionable. What are the current CPU? Let's just check. Coffee Lake cycles for 64-bit float multiply. I just want to know. Like, just tell me the fact. I guess it depends on whether you're using like, you know, AVX or what. Oh God, we're at the beginning of the manual. I don't, like, when did it become so impossible to find useful information on Google? I don't. Peak Google was like 8 years ago at this point. It's like 5. Check the Agner fog sheet. Well, updated 2019. All right. Wow, he's like doing some stuff. IML, no, not IML. Are the float in their own place? Floating point. FML. Latency 4. Right. That's for AMD. I know, but it's a reasonable processor, right? Like I don't have to look at Intel Coffee Lake. That was just an example that I was using to search. Okay, what's this? Are we still on AMD? K8. Fist P, I remember that. Sine cos. Where's our FML? FML 4. Broadwell. FML. LOL. Wait, what are these? Latency 5. But they're all one they're all throughput 1, latency 4 or 5. So like, I don't see the point in trying to do something tricky. fmul is old instruction. That's true as well, actually. I don't remember what the new ones are, even though I had to implement it. Let's see what I use in the x64 backend. Okay. So we say mul s something. Oh, and we weren't making sure it's 64-bit, by the way. fmul probably isn't even 64-bit. I don't even know what instruction this is. Oh, here we go. Look at all these instructions, everybody. Mul ss, mul sd. Okay, right. 3. I mean, it's close enough that I wouldn't try shoving a number into the exponent. The names get more insane. Oh, yes. Oh, yes. All right. Anyway. Let's go back here. Ain't no party like my Nana's tea party. Okay. I mean, we have a sign function, except for some of these things. We already have this pol level, except we renamed it, right? Polynomial eval. So this time, okay, we're going to need load exp. We're going to say so this loss, I don't think is defined. Two overloaded definitions, same procedure, can't have identical. Okay, so what I was about to say was let's call this something different for now, and we can bench it against is finite. All right. Lost the, let's. Okay. Load exp. Right, it was load x z minus 1, yeah. All right. Let's make our little test program do some signs. Okay, instead of, we've already got a loop here. And instead of calling atan and atan2, we're going to call S1 is sine theta, S2 is my sine theta. And then we're just going to say ain't no party like my Nana's tea party. You need y divided by 16 too, right? Didn't I do that? So that's that load exp. I left all the comments in, right? Load exp. Multiplies x by 2 to the n. So this load exp is 1 over 16. This load exp is times 16. Have I considered adding something like, did you maybe mean is finite instead? Yeah, I've thought about that. It's just, you know, there's more important things right now, but we'll probably do that eventually. Why is lost the... Okay. So like, do we really want cosine also? Okay, well, let's try this. J cannot be 1. I mean, it sure looks fine. I am calling two different functions, right? Yep. And I'm printing two different numbers. Okay, they are different. But not for a while. Is manual sine plus cosine still faster than f sin cos if you want both? I don't know. Print J's and see what values you get. Well, we can certainly, also, we can assert J is not equal to 1, right? Oh. We're going to have to do that for print as well. Really? Two, zero, two, 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 zero, zero, zero. It's like it just goes around, right? It's quadrant 0 or quadrant 2. I mean, I guess that makes sense because for sine, you need one positive quadrant and one negative quadrant. Same for cosine, really. In fact, 0 and 2 would be fine for cosine as well. Anyway, we go around the circle a couple of times here, and we only do 0 and 2. Assert j is not even. Assert not j and 1. Oh, assert that it isn't even. Wait, what? No, that's going to fail immediately. You mean assert it's not odd, right? Multiply is way better than loadx. Oh, okay. Yeah, I mean, I'm not surprised. That said, like, look, the compiler may not be doing the best thing for loadx, right? So that might affect the results. It's just, it doesn't sound to me like a modern thing to do. You know, I definitely, and the reason why I came to that conclusion so fast is when I started out in games, we did that kind of stuff all the time. Like, you didn't want to use the FPU because it was slow and sucky, so you did everything in integer that you could. But the time for that is long past. Okay, we're going to put a comment here. Original CFees put j is equal to 1 here too, but it appears that that is impossible, so we took it out. So me and Twitch chat took it out. Now Twitch chat is implicated. Okay, so why don't we just do this? Is there possibly some kind of numerical accuracy thing? Like, that's weird. All right. I mean, do we get different results? 5, 7, let me just paste this. It's the same number down to the lowest digits. All right. Well. Can't test div because the compiler refuses to output div instead of mul. Even in debug build? I'm actually not that surprised. You would have to, like, literally use inline assembly to get a div. Oh, more even without fast math, I see. Yeah. Ain't no party like a name is to you. Let's do cosine. Okay, well, let's put sine. Whoops. This is our sine, and we're, again, this is a little bit questionable, but like, cast float 32, sine cast float 64x. All right, and then we go to math, and we get rid of that, and we get rid of that. Look, we're playing a video game with sine. I mean, I guess it works. Look, we have an editor I'm sure that I'm calling sign in here somewhere. We could put a printf in the middle of sign. Let's do that. That's so stupid. Like, I'm not used to having source, not source access isn't the right word, but I'm not used to like playing with the source of basic functions like this. Like, I've definitely had source access to these things, but they're always like very inconvenient to change and tucked away, and now they're not, right? So like, let's see what happens. Oh God, we're calling sign a lot. Yeah, we're calling sign mostly of 0, but sometimes of other things. We're calling sign quite a bit. Maybe we shouldn't be calling it as much as we are. But you know, we're probably calling it to generate rotation matrices for every entity that we render, right? What happens to the game if sign returns a weird value? Do you want to find out? Let's see. Let's say x equals minus x times 3.7 plus 0.3. All right. I don't... Should we put a square in there? Like, I don't even know. All right, what's going to happen? I'm really scared. Whoa. 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 It's like you're living in some universe where the laws of math are different. Whoa, I can't see anything. Oh God. Okay, I can't. Let's delete the sky. Okay. Well now, oh, wait. Oh, okay. I can kind of see the guys. Right there. Okay, this is crazy. The raycast is happening on the CPU. So it's getting the same screwed up coordinates as the renderer, and it matches. That's great. All right, pulling out the C libraries math. Sort of. Like, you know, different C libraries use different things. And so I picked something a while back that looked pretty good to me. Like, it looked like it wasn't a ton of code and that it was reasonably clean. And so we're doing that. Thought it would be much worse. Okay, so I will point out that the pixel shaders call sign, and that's on the GPU. So we're unable to screw up that sign. We're only screwing up this sign. Okay, let's make sure that we repaired the damage. That was fun. Hey, my guy isn't doing weird things. All right. Look, I can move normally. It's great. Okay. Crisis averted. We're going to be Mycos. And Mycos, it's like Greece. Wait, he's not setting sine. Right, because it's cosine. Is this... Oh, down there. I mean, he's sort of making it look like sine sin, right? Let's introduce this down here. If x is greater than losth, so y is floor x divided by pi over 4. Okay. Z equals y times 1 over 16.0. Okay. Integer and fractional. This is all the same, kinda. I mean, we almost can combine these into one function and just make it a compile time. That might be a fun thing to do. If j is greater than 3, j minus equals 4. I mean, it's a little different, but not that different. That might be why it was checking for j equals 1, because maybe that's relevant here. And he just wanted to be able to copy pasta it, right? I don't know. Okay. Like, let's look at this next to sine. Cosine on the left, sine on the right. So there's obviously the x is equal to 0. If isnan x, if not finite, make argument positive, but save the sign versus make argument positive. I kind of want to combine them into one function, guys. And I think that'll be fun, because they're mostly the same. We'll use the power of this programming language to do that in a nice way. Yeah, no early outs for 0 for sure. Let's put this back where it was, actually. So the J handling is a little... Hold on. Let's resync these. So, yeah, it's a little different. So this is... Wait, why is it I here and J here? And then J is I and 7. Like, why do you have two variables? Was this an earlier version of the function and this was later? Because we don't use I down here, do we? We do not use I. down here. It's basically the same code, guys. Except for where you flip the sign. Okay. So I is even again. Okay, wait, let's verify I doesn't get used. It doesn't. So let's just make this J. I think this just got done to this because this didn't even say and equals. I was wondering about this, right? It says J equals J and 7. Which I was like, why didn't it just say and equals 7? Because it's C and he uses lots of these operators. And the reason is because this used to be I right here. And he replaced I with J, but then didn't do this part. Okay. So like, let's make the formatting the same. I mean, like this, there's this extra here. But it's the same. J is 0 or 2, right? That's all. It's for the same reason, right? It's even. It's not greater than 7. It's not greater than 3. So it's 0 or 2. This could just be if J, right? This is like a fun Zachtronics game right now. Inline assembly div benchmarked. It comes in about halfway between mul and loadexp. Wow. So loadexp is really slow is what you're saying. Because we consider div to be pretty slow. All right, so we're going to first make sure this compiles, which it doesn't. If def. Yeah, we don't have if def. Oh, because of this stuff. Okay, this appears to be extra. Okay. All right. So we're going to go back to our little test program here, and instead of sign and my sign, we're going to go cos. Like this. And it looks the same. Wait, it's exactly the same. What? Okay, hold on. Did I screw this up? Cos. My cos. How is it exactly the same for cosine, but wasn't for sine? So for sine, oh, we don't have my sine anymore. All right, well, rip. How are these bitwise the same? Did I actually mess something up for sine and I should have been bitwise the same? Sine is harder to be precise. Really? I mean, they're the same code though. Like, dude, it's exactly the same source code. How is it? I mean, I understand the general argument that it's harder to be precise, but like, sine of x is cosine of x plus pi over 4. So how is it really hard to be precise? I don't get it. I don't understand the argument. I mean, maybe there's just something I'm not getting here. It is very close to the same code. I mean, I understand the limit as theta approaches 0, sine theta over theta equals 1. But like, that's not what we're talking about, because we're just going around and around the circle. Plus offset destroys the precision of near zero values. Yeah, but we're not giving it near zero values. We're giving it values all over the place. Now I'm worried that my sign is wrong. Like, literally every single number is the same. For all I know, this is what Windows is using for its sine and cosine. It's quite possible. Which would mean that my sign is wrong. Let's go back to, let's drop the status of this to my sign for a second. So here we have libc, and here we have us, and wait, now sine is exactly the same. I thought it was different before. Am I tripping? I thought it was different definitely when we were doing this. No, I'm tripping, guys. So maybe they're not the same implementation. Maybe they're just both accurate to the last decimal place. I'm still calling my sign both time? What? No. What do you mean? What do you mean I'm still calling my sign both times? Oh, right. Okay. Yes, okay, this thing, but that won't matter. So this actually doesn't matter because this is sine of float 32. And we should be calling float 60. Oh no, it's float 32. I never specified 64. But it's still the same, guys. Oh no, it's not exactly the same. Look, we're off barely. Oh, we're off barely in cosine. Maybe I just didn't see. Okay. We have tiny differences when we do float 64. We didn't have tiny differences in float 32, I guess. Tiny, just little baby differences. There's another one. Tau doesn't make it double. Maybe it does. Oh, but, well, this might be. Actually, no, tau is probably single precision. But this was just -7. -7 is definitely single precision. And then theta is just this, so theta was single precision for sure. Like type inference doesn't go backwards, like from here to there, you know? It was significantly different last time. Well, I don't know what to say. It works for me. It works on my machine. Did I check in the sine code yet? I have not. We checked in tangent. That's it. It works on my machine right now. It was different from the 6 digit when I checked before. Yeah, I remember that, and I'm confused. We did change like the ZZ thing after that, right? Didn't we? So I don't think that would matter. But like this part, and we added the parentheses, right? So this was different. And no, it's just last digit here, man. Works on my machine. Wasn't it float 32 earlier? We were just printing fewer digits before. Oh, well, yeah, the variable was float 32. Oh, wait, let's try that. Let's actually do this. So this is going to go to the float 64 rounded down to float 32 on ours. And maybe libc here has its own implementation of single precision. That would be a reason to get substantially different answers, I guess. Nope. I mean, so the thing here is we're not, like we're printing out a ton of digits and this is more than you actually can store in a float anyway. So you might expect more of a difference, but it's literally exactly the same. What is up with that? Oh, these aren't exactly this. Oh, yeah, they are. The differences we were seeing before make me think you were comparing floats and doubles. It could be. It could be. Let's do that intentionally, right? Let's say that it was float for libc and double for us. Yeah, that, okay. This looks like what it was. Right? Like right around here it breaks. That is, thank you for suggesting that. That is what it looks like. Okay. Works on my machine. Benchmark time? No. You don't benchmark sine and cosine, dude. Like, if you want your game to be fast, don't use sine and cosine. Okay. This is great news, though. So let's take over for these, sine and cosine. We're going to check in with it like this, and then we're going to combine them with wonderful compile time technology. It'll be great. All right. We are now running the game with sine and cosine in the new implementation. C# is a good language or not? I mean, I've never used it. Don't ask me. It depends on what you want, whether anything is a good programming language or not. What are you looking for? If you're looking to manually manage memory, C# is not a good programming language. If you're looking to program Microsoft things, I don't know, then it's not bad. We're going to have to do a Benny test with everything before the night is over. Glad your BS detector for when garbage float digits are being printed still seems to work. Yeah. What we could have done is print out the hex floats for everything, right? And then you could actually see the bits. Heard you say Benny test is faster last stream. What did we do to make it faster? We got good. We went to the gym and we lifted weights. For sine and cos to use an approximation. Okay, so this appears to be an approximation with a polynomial, and it seems to me that they chose enough terms of the polynomial to give you the right answer to 1 or 0 ULP. If we go read the documentation for this, it'll probably tell us. Okay. Let's Benny test this, because our Benny tests only take 3 minutes now, plus the time to make a release build. They're fun. We like Benny testing. Welcome, rating people from Paperfan Games. All right, here we go. Maybe it's even faster with our new sine and cosine. I doubt it. All right, we're going to time it again. Ready? People may not find their way without a real roadmap for engine development stuff. I mean, maybe, but look, what I know is what worked for me was to just sit down and make video games. That's how I learned to make video games, was literally to sit down and start making them. Once in a while, I would look in books or other references. They're very helpful sometimes, like when you don't know what some math is or something like that, okay? But you need to have the impulse yourself. It needs to be in you. You know when you watch the cheesy fantasy movie or whatever, and they say, Billy, the power was inside you the whole time. You can save the world with your abilities. That's video game programming, all right? The power is in you the whole time. What is a torque? You don't know what a torque is? Bro, look it up. So, and okay, here's the thing. Here's the thing about books about video games. There are some that have true important knowledge and some that have knowledge that is of a weaker, lower class. So the books that are like, here's what quaternions are, right? Here's what the math is for how you rotate objects and project. Here's how you use ATAN2 to do perspective projection. All those kind of books, that's real knowledge, right? Fake knowledge is like, here's how you structure your gameplay code so that it's good or whatever. Like that's opinion, and unless it's from someone very, very, very experienced, it's probably largely wrong, okay? And the problem is that most publications are of the latter kind, right? What you really want to do is be paying attention to things of the former kind. All right, we're going to finish soon. .308. I accidentally tapped it, so I got a little bit of an inaccurate. All right. Yep, same number of fails, so we are good. We have replace sine cos to eliminate libc dependency. Okay, so now we're going to do something fun. Whoops. We have a no check-in. We're not going to do something fun yet. No check-in. Yeah, forget that. And then this, we don't, whatever that was, we don't care. Still compiles? Yeah. Boom. We still have one. Bro, this is crazy how many no check-ins. Oh my God. Okay, basic. That was just for our printf. No check-in. Remove flag. I think we might want to do that, but... And then, these are fine. All right. I'm not a fan of ginger in my tea. I've had ginger tea sometimes and I dig it, but I don't think I've tried ginger as in like fresh cut ginger in a black tea or anything. It could be good. Okay. What's a no check-in? It's just if I want to make sure that I take care of something before I expose what I've done to the rest of the team, you say no check-in. It'll prevent you from checking in the code. And then, etc. Okay. So here's what I want to do. I want to have a function called sine or cosine, all right? Maybe even tangent. Like let's look at, is there like a tangent dot? I bet it's almost exactly the same, right? Tan coat. I mean, it's not exactly the same. It is broadly speaking the same structure, but the math is different. Okay, so we're not going to worry about that. So we're going to do a function called sine or cos. And we're going to say is bool. All right. So sine is going to call this with true, and cosine is going to call it with false. But this is guaranteed to be compile time, and so you can static if all of this, right? So you can say, right? So this was sine, and this is cos. So we're going to say if is sine, we do that. All right. And then our isnan, our finite check. And then sine, if x is less than 0, x equals minus x. If is sine, sine equals minus 1. See what I'm doing? Do you see what I am doing? And then this is the same. 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 Like, how is it so much the same? I don't understand that. Am I missing something? It's like literally exactly the same. Oh, these are swapped, dude. Oh, yeah. That's the difference. That's how they do the plus pi over 4, is you just give it a different table. So we could probably do this shorter. Right? But let's just do this for now. Okay. All right, so that's sine or cosine. And here, whoops, we're just going to comment these out for now. Okay? So sine is going to be return inline sine or cos x true. Cosine is going to be turn inline sine or cos x false. That's it. And we save half the code. Forgot to use coscof. Oh yeah, good, 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 good. Thank you. Thank you. So obviously we can make this shorter, right? Etc. Wasn't the logic on that if different? Which if? There's a few of them. So this was cosine, right? If j is greater than c, sine is minus sine is... Oh, this one. This one. We need this. Okay. If not is sine. There's also a missing ZZ times 0.5. What? Oh wait, these are swapped. I did the wrong thing. I was looking at. Yeah, okay. So this is actually, maybe we do leave it, right? So this is actually here with Kozkov, right? And this is actually here with Seinkopf, right? Is this actually better than just repeating? Yes, it's a lot better, I think. Maybe. I don't know. Like, maybe. That if statement still isn't testing. Which if statement? There are many if statements. Oh, wait, this one. No, that's J and 1. Are you getting these crossed? Like, you can see how the code was diverging between the two versions. Like, the comments were a little bit different, even though it's the same function. I mean, I added a little bit too, but, you know, despite that. If j is equal to 1 versus j is equal to 2. No, okay, no, this is different on purpose. So this one, we took out the j equals 1. J can't be equal 1 here for the same reason. We just didn't bother deleting it because I knew I was going to combine the functions. This is useless. This doesn't do anything. Right? This is fine. I mean, if you've been on the stream only for a little bit tonight, you wouldn't have heard that discussion, but we discussed this a bunch and we tested it out, and it's true. The j can't be 1 here. Yeah, it might have been originally one function and then he split it in order for better performance. But part of the point of this language is you can do stuff like that without sacrificing performance, right? You can keep the code from diverging in that way, and it's less for people to read and all that. Okay. I mean, I kind of just want to try it. Maybe I made a mistake, but so it compiles. Oh, there's no mycos anymore. Got rid of that. Actually, let's put it back for a little bit, because I want to test versus a reference, right? So we're going to put back cosine and sine, and we're going to go my Miss American Pie drove my Chevy to the levee, but okay. All right. I mean, I see matching numbers. So Metaprogramming feature. Feel like the last block would be clearer if it was if sign. Let me see. Let's delete this stuff. How many lines of code did we save? Approximately the size of one of these. So like about 300, wait, from 388 to 445. So about 60, right? That's not too bad. Okay. So you feel like the last fourth from the bottom is different on last digit. Yeah, that was true before though. Like we expect last digit difference. That was true before we combined the functions. There'll be some other ones up here somewhere if we look enough. Like here. That's fine. We're just saying that's due to different implementation. Okay. I'm going to put it in the, yeah. So this doesn't even have to test versus equal to. It can just be if j. Okay, so what were we saying? The last block would be clear if it was if sign, if else, else. Oh, you mean move this outside? Let's see what that looks like. So you're saying instead of this, we go if is sign out here? Let's see. Let's get rid of this. Else. And then like this. I mean, it's substantially more code. Although we don't really need the braces, so we could compact that in this. So we could do, oh, hold on, in this as well, right? Is that what you were suggesting? Is if j faster than j is equal to 2? Yeah, probably a little. Problem with transcendental functions is that it's impossible to get the last digit more or less accurate without computing to potentially infinite precision. So yeah, it's probably kind of like, you know, string to float, right? Where there's always some digit, like 5,000 digits out, that could cause you to round up for some cases, right? That sign equals minus sign could go in the last. Yeah, because we don't use sign until the end, right? And actually, this can just be if j. We don't need this sign variable, right? All we do, oh, we set it here too, never mind. Okay, hold on, I feel like this is not right. I mean, I don't know, okay, hold on. So now we have to go back to our sloppy C. Like, look how unreadable this is. Okay, so for sign, we had the j greater than 3. Sign equals minus sign j is minus equals 4. Okay, so for cosine, j greater than c, oh, it was just in the other order, but it was, I don't understand. Oh, this is the other sine equals minus sine. I was like, shouldn't we have one for one case and one for the other case? And we do. We do. Okay. Could shrink it better if you could do a temporary expression on the compile time test. A ternary expression. Well, you can. That is a secret ability that we have too. Let me finish doing this one, and then I just want to compare. I want a fair comparison, right? Right. So we're kind of saying that. We're also saying that we could do if j. These look the same to me, right? I guess this is probably better, right? Right? From a compile time performance, this is slightly better because it's only one static if instead of two, but this is probably better, right? Is sine j not j? Oh. I mean, we can... That's breaking my brain a little bit. So first of all, we know that j is either 0 or 2, right? So we could do this. Let's put no check-ins on all of these. Right. So I'm trying to think about how to insert an exclamation point, which I don't think, like we could do that, but it would be messy. But we could do k is, if x is sine, then 2 else 0, right? And then we could do this. Although, I mean, that's a little bit more like obfuscation to me. I don't know if static if x works right now. Let's actually see if this works. It doesn't like then. Yeah, if x is a little weird. Static if x is a little weird. Yeah. I mean, does that even work? Oh. This is really ugly. So we can do this. We can do it in various ways. It's just how messy is it? It also feels weird to have those verbose. Yeah, on the other hand, yes, it's a verbose thing that feels weird to have duplicated, but on the other hand, it also kind of reminds you of the way sine and cosine are like one quadrant apart, right? I don't know, man. That's getting very complicated. I don't know. I mean, I kind of like this. I just wonder if it's a little bit too much like showing off. But it probably is more understandable. Let's do this for just to make it. What is J? What is it? J isn't even S64, it's S32. So let's make them the same type. In fact, we could make isSine S32. Like if we want to be, this doesn't matter because it's compile time, so it doesn't cost us anything. But instead of being bool, it could be S32. And then we just multiply. Can you return both values and have the wrapper functions aside? No. I mean, that would make, you could maybe make some super ugly macro that does that. Macros are kind of not fully baked yet, so I don't want to go there. But also, there's a few other differences throughout this function. You can't just return one piece of code or the other. And if you actually return the numbers, you're not saving the work. The whole point of what we're doing right now is that we're generating two functions at compile time from this one function just by toggling this argument. And there are several things that are different, right, between them. I kind of like this one. This is a little bit showing off. Let me see. When we get to this point, J can only be 0 or 2. Sine, let's put that comment up here. When we get to this point, J can only be 0 or 2. Sine and cos. Want the same behavior offset by one quadrant. Each increment of J represents 45 degrees, so 0 and 2 are one quadrant apart. Sine and cos want the same behavior offset by one quadrant. So we use the value of k computed here to decide which quadrant to do. The various negations handle the rest. I don't know. You know, this is the kind of comment that I wish had been in this code to begin with. If isSine J equals 2 minus J, that adds more code though, right? Or did you suggest that a long time ago? J equals not J followed by J test should get optimized out. You think it's clearer than treating bool as an int? Yeah, that's probably true. Okay, so we have to do, so if, actually it's, we could maybe simplify out this not, but it's if not is sign, J equals not J, should get optimized out alongside the if below. Okay, so if J, else that, right? Okay. Yeah, that is clearer, honestly. Or we could say J equals J XOR is sign, right? Or not is sign, yeah, whatever. Did we break it? J equals, right, so not J is a Boolean. So I mean, it's one extra integer operation. Do we really care? Maybe. Right, but then this is an extra. Comparing to 2 is an extra integer operation as well, and we sort of removed that, right? 2 minus J is less likely to get optimized out. I mean, I could do this. I just don't know if the type conversion, you know, makes it. I mean, I guess that's fine-ish, right? It's not the same, not 0 is equal to 1. I know, but we only care if it's 0 or non-zero. Because, so it could be 0 or 2, and we're just saying 0 or 2 is just like 0 or non-zero for the purposes of this code, right? This is great that, like, we're substantially improving this code. Okay, look, first of all, Stack Overflow copy and paste guy would never have noticed that J can't be 1 down here, right? Because remember, the if statement we were originally dealing with was this, which this trick wouldn't have worked with if it was that. But we noticed that J cannot be 1. And that enabled this further optimization, which is great. Sin cos is way less faster than sine comma cos than you thought. Oh, how much? What difference are you getting? I mean, it probably also depends on the implementation, right? Are we optimizing our own trig functions? We are making ourselves not rely on libc for trig functions. Yeah, okay. I like Sean's suggestion here. Wasn't there some other stuff? So this sine thing here, this one right here. So first of all, j is 0 or 2. So again, we can do this, and that will not change the meaning. Right? Right? I don't see any problems. I mean, honestly, we should be comparing, but whatever. We're using the eyeball comparison. It's all good. And then we were saying, so sine doesn't actually get used until down here. So we could move it down there for sure. Before we were talking about combining it with this if, but that maybe makes less sense now. We could. Okay, wait. We also toggle j. But we would still prefer to use the unmodified j because of pipeline latency issues. But we could, okay, so instead of doing this, we could do the following. Right. Or, because we don't change j after this, we could leave that what it was, and we could bubble this down to here and get rid of the, oh, we can't get rid of sine actually because other things set it. All right. I mean, this does seem mildly better than having two different ifs. You know, although if you were making the case that we're figuring out sine finally by here, then it's maybe more topical to put it up here. I don't know. Toggle j should get optimized out anyway. Yeah, that's true. So it wouldn't matter. And, you know, it obviously doesn't matter if this is not j or j because you just use a different branch instruction. You negate the condition on your branch. I think I like fewer static ifs, right? Because the static ifs are like, here's the difference between sine and cosine, right? And so if we have one less of those, then that's pretty good. Did we screw it up? It looks the same. So guys, this is the first example that I remember of using this kind of feature in not my own code. It might not actually be the first, but it's the first that I remember recently. Like I write code like this sometimes where I'm like, I'm going to architect this so that there's a core function that we can polymorph at compile time to do what we want. But this is the first time where it was like blatantly obvious that someone else's code like really wanted this. This is a little weird because like y gets changed here. That's the last time y gets changed. So you kind of want to compute z up here, but then maybe it also doesn't get used till down here. Maybe we should compute these down here, right? Like, just like they should bubble to one place or the other place. You know what I'm saying? And then that puts this close to this again, right? We're really improving this code, chat. It would be easier to eyeball if you put S1 and C1 in one row and S2 and you're correct, because the minus signs would line up, wouldn't they? Wouldn't they? I mean, honestly, we should be epsilon comparing them, right? So the origin of this code was it used to only do sine, right? Or it only did cosine, one of them. It only, and then we added the other one. All right. But yeah. Oh, and it's also easier to compare the digits because they're on top of each other. It's way better. Yeah. Way better. Way better. Did I change C1 or C2 to use the new function? It is C2 and S2. So basically the bottom line is the new function. Top line is the old one. Top line is libc. Bottom line is our compile time polymorphic cool language features. As far as I know, not any other language really has in this. You could probably make this happen in some of these languages, but it would be uglier, I think. Can the minus signs negating each other be optimized? I mean, maybe. I mean, we have this weird thing where if j is greater than 3, so if j is greater than 3, it could only be 4 or 6, right? So this is if j is 6 only up here. If this value of j is 6, then we negate sign. So you could sort of say if j is equal to 4, sign equals minus sign. But then you have to check. See, the problem is this. If j is equal to 4, j is 0, and whatever. You know what I don't understand, guys? Why is... Maybe I'm too tired tonight to really think this hard about this, but like, he's doing this as 45-degree increments. But then... I mean, I guess it's all to get this y, right? That's why we're doing it in 45 degrees. Something. Okay. How do the performance metrics compare to the libc version? It's a good question. The problem that we have is we're at a disadvantage of testing the debug build, but we could test the release build. The debug build, of course, we get all sorts of debug stuff in here, but not in the libc version, because we're compiling against release libc all the time. But we can do this. We can do the fun thing that we did. There might be a population count. Count the 1 bits in J and look at bottom bit of that result. There's only 2 unique octants. They're not adjacent, I think, because if they're adjacent, then they only work for sine or cosine and not both, right? Like, if you're only going to distinguish between two quadrants, then you want, like, quadrant 0 and quadrant 2 are both opposite sign for both functions, I guess. I don't know. I'm not sure if that's the reason, but that's the sort of hand-wavy explanation I have in my head right now. 2 octants. Oh, you mean octant? You mean 2D octant? Okay. I was thinking 3D. Okay. Let's do this funny thing like we did yesterday. So yesterday, or was it this morning? It was this morning, I think. We did a fun thing where we were calling ATAN 300,000. Oh no, we were parsing a floating point number. We were parsing a 64-bit floating point number 300,000 times per frame, and we were still more interactive than Google Chrome, right? I mean, we were getting 60 FPS. Well, during 60 FPS, we were only doing it 100,000. We were parsing 100,000 floating point numbers per frame and rendering our game at 60 FPS, just as a stupid benchmark. All right, let's do that again, because I want to know. All right, so we're going to go to simulate again, and we're going to go stupid. Right. Oh, here's our old thing. This is what we did, is we made a compile time array of numbers, and then we ran these things that parsed them all, and it was 40,000 each. So it was 120,000 for all three, and then times 3, because we were calling this 3 times per frame in debug build. All right. So stupid is going to be stupid. Let's call bench sign bench my sign bench, right? All right. And I'm going to make an array of globals so that it doesn't optimize it out again. And we're going to use the same num iterations. We'll use the same table. Let's even use we'll just assign assign theta. What is theta? Well, I don't know, something like that. That's not going to be enough iterations to really make a dent. I don't know. Okay. All right, let's just debug build that and make sure. Okay, we did it again. We screwed this up last time too. Oh, array bounds check failed, of course. Right. This is x64 build, which is extra slow at runtime. Let's see what happens. All right, stupid is taking 300 milliseconds. I didn't put profile zones in there. And of course, I forgot as well that we need to name it, because otherwise it'll go away in release build. All right, let's just make sure that worked. Okay, so we see my sign and sign. My sign is way slower, but that is no surprise because sign is a release build sign in libc, and my sign is a debug build sign, not only with the x64 backend that's generating hella instructions, but with like array bounds checks all over the place and all kinds of stuff. Let's try LLVM. That should be closer, but still we should lose. But then for release, I honestly have no idea if we're going to be faster or slower. I didn't necessarily pick this because it's reputed to be fastest or anything. All right, we're a little better, but still not great. But that doesn't matter, I hope. We'll do the release build and see how it comes out. All right, people. I guess we're not going to rewrite the core compiler thing tonight. We'll do that in the morning, maybe. What's the non-release LLVM build for? I mean, it does generate a somewhat faster running executable. It used to be that it had debug info and x64 didn't, but then Josh put debug info in x64. So now they both, I don't know. All right, so we are a chunk slower than libc, interestingly. I mean, I imagine they probably SIMD optimized theirs or something, right? Like, I would guess that they're doing some detection and some AVX stuff or whatever. But I don't actually know. Is that warning not easy to eliminate? The one when I compile? That's just this one or this one? These are both just things that I haven't done yet. It's just, I have a lot to do. Right, so here's the thing is, this sign is like almost 3 times slower. It's about 3 times slower exactly than the libc one. But we don't want to use libc. You know what I'm saying? Now the thing is, what do we do? So this is the first time where we replace stuff. I guess I didn't benchmark tangent earlier tonight. This is the first time where we replace stuff and it is actually slower. Like when we replaced string parsing, it was faster. So now this is a dilemma, right? It's like, do we maintain the libc crutch, or do we just put in the notes, look, this version at the time of authoring is slower by about 3x than the libc, but so if you want absolute speed, you could use the libc, and eventually we're going to SSE ours or whatever, right? We do turn off array bounds checks, right? Let's see. Array bounds check mode off. Yeah. Oh, you know, we don't need all this anymore. Okay. This is definitely a dilemma. Profile and optimize your implementation. There may be some optimizations even without SSE. I don't think so. Not big ones. Like 3x. 3x is a lot. We're not talking 10%. We're talking 3x. That said, some of this, like, I don't know if the libc version is checking for all these cases. Maybe it is. Maybe it's not. So, okay, I mean, no matter what, this is progress of a kind, which is like, look, we both are moving off of libc and have consistent implementation across platforms, which is important. So like, hey, when I switch from, you know, Windows to Linux, my math functions don't mysteriously change for no good reason, right? That's actually a very good thing. But 3x performance is a lot. I mean, even though you kind of know sine and cosine are going to be slow and you don't really call them that much, it's still a lot. I looked at the libc code. No, I mean, does Microsoft give out their libc source? I guess they do. I guess like if you had MSDN back in the day, which I did for a while, you could get that. I don't know what the status is now. It's unclear why they show 2x speed up. Well, I mean, the compiler shouldn't be generating 8087, right? The compiler should definitely be using modern instructions here. And this doesn't seem that slow. Like, it does this polynomial eval, which isn't that much code, and it does it 5 times, right? We could unroll it instead of making it a loop. Let's try that. I mean, I don't think that's going to help, but like, we could do this. Actually, look, this is crazy because we know the array and we know the number of steps, and you can just unroll the array into there, right? Like, okay, let's just do something really stupid. We're going to do this. All right. Actually, let me, hold on. Let's actually save the code here. Okay. because all this is doing is the following. Right? Ands equals that. And then one, 2, 3, 4, 5. This is literally all this code is doing. So you can see right. And then you might even, I don't know. So that'll be active for one quadrant. Whoops. Let's do release build again. See if that's faster. Muscles libc breaks that serial dependency chain by computing x times x and x times x times x times x separately. I would have to think about that. My brain is not doing the refactor for me right now. Okay, let me see. Okay, this is faster by, 3%. So we can make it probably another 3% faster by doing that to the other function. It's just, I mean, we are starting to pollute the code at this point. I mean, we could just write instead of saying ands equals ands times x plus whatever, we could just write out the whole expression, right? That wouldn't necessarily generate faster code, though. You have to rewrite the polynomial to use explicit x to the n. Right. Then you have x squared equals x times x fourth, shortens the dependency chains, allows them to overlap. Interesting. I mean, I guess we're saying we're doing this, right? I just, like, the problem is, from what I was saying yesterday, like, code understanding does go down, right? So here's the thing. If I'm saying we're going to do an SSE version eventually anyway, or I guess you were saying that probably doesn't help. But if we were going to do something that uses some kind of machine instruction specifically to be substantially faster, like if we can match if we can get 3x somehow, right? Clearly 3x is possible because Microsoft libc is getting it. Whatever they do, if it's very different from this, different enough that you want to test for machine capabilities and say, do the fast version, otherwise do the slow version, then I don't also want to do this. Like, I'm fine if the slow version is the simple version here. And then we have a fast path. Like, I don't think making the slow path better is worth uglying things up. You know what I mean? That's what I'm thinking is there's no way, like, even if we break a dependency in here, it's not going to give us like 5x speed up this or 3x speed up. So I'm kind of wondering how they possibly get 3x speed up. Like, I don't honestly know. Like, maybe you can use the CPU sign instruction. Like, isn't there like a limited precision sign? And you could use that to give you an initial thing and then just refine it, maybe, somehow. You would do it just to see what speed up is. Yeah. Okay, hold on. Let's do a thing here where we check this in. Because it's a good like beachhead for, let's run the tests. We haven't done that in a long time. Not a lot of them use trig, but some of them do probably. I do wonder how many no check-ins I have. Hopefully none. I don't see any. Look, I never have no check-ins. Come on. Come on. What kind of person do you think I am? All right. So this is a very good, we used, oh yeah, we still have libc sign. Okay. You know what? This is actually would be a little bit of a regression if we check it in because we had taken out the libc sign before and now we're putting it back in. So what I'm going to do is this. We're going to switch off the libc sign by default. And maybe that'll motivate us to make ours faster anyway. We're going to do this. We're going to keep these for now so we can call them and compare against them. So we're going to do this. And then ours is not going to be ours is going to be the default. That way we better make it good, right? Okay, and then our test here is going to call sign for us and libc sign, right? Makes sense? Is IndieFund still active? Yes, it is. IndieFund just funded somebody in the past week that I led the funding round on. Oh, we have to, right. So the error there was just, if you don't say what the name is out here, it says it's the same as this, but this is obviously not called libc sign. Oops. All right. Okay. So we'll check that in. And now that's not a regression. We've switched over to our new code, but it is a bit slow. Okay, I admit. Okay. Factor sign cos into one function. Okay. Let me warm up some tea. And then we'll go on. I should look at the muscle libc version and see if it's like the same coefficients or what. I just realized something else. I did this wrong. So here, if we put the inline on the inside, we're sort of blowing out the code size because we're generating. I guess not. I guess it doesn't matter. I was going to think maybe we should just put the inline here so that the collar gets inlined and then. No, this is fine, actually. We split over multiple files to share code between Sign and Coast, which are themselves in different files. Yeah, well, with C, you got to do what you got to do, right? Several big publishers have programs they call IndieFund. No, I haven't heard of that. I don't think big publishers do, because I know what the big publishers' programs are called, and they're not called IndieFund. So you might be thinking of small publishers. Do we hire interns for free? No, we do not. Yeah, you might be thinking of small scam publishers that have things called IndieFund. Like, I don't know. Be careful who you deal with. Why did you make Eval Poly Koskov 5 instead of Eval Poly with Bake Koskov and 5? Well, because I'm not absolutely sure that we constant evaluate array subscripts right now. We might not. So I was putting the numbers directly in the function because that way I definitely know for sure, right, that happens. Yeah. You should hire to learn people the right. What? That sentence doesn't even make sense. E.g. Fox. I have never heard of Fox. Who is Fox? You mean Fox the TV people? There's a publisher called Fox? That beeping come from the stream. It was from the teapot, probably. How developed of an idea should you have before you go indie? It's not so much about the idea. It's about, are you ready to work hard and get stuff done? You meant teach. Like, look, here's the thing. When people are not, I don't know. We just have a lot of problems. Sometimes we hire younger people and they're amazing, and sometimes we hire younger people and they're terrible, right? And I don't feel like not paying someone is somehow magically going to make them more toward the good side. It feels more toward the not take it seriously side, right? Fox, the TV publisher, has a games division now. Why would anyone sign with them? That makes no sense. They're going out of business real fast. Like what? Fox Games Publishing. Is this a real thing? Fox Next. Wait, no, that's an old thing. Wait, there's a website. Games. Marvel Strike Force, Avatar, Pandora Rising, and Aliens. Yeah, rip. This publisher is going out of business. All right. Do I have an idea of what I want the standard library for the language to be? Okay, look. There is not a standard library for this language in the way that there is even for C. Like for example, in C, there's like a standard file and a standard way that you're supposed to fopen and stuff. Like here, it's like, look, we'll give you a module that has something like that. But if you don't want to use it, just use your own. It's fine, right? It's separated out from everything else. You don't have to buy into both of them, right? It's source level, so it's not like you have to link against a giant thing. So what we are providing is examples of how you might do things. And you're free to use them, you're free to not use them. We are definitely not C++, where they somehow feel like every possible function that you might want to call has to be in the standard library. That's absurd, right? It's terrible. So I don't exactly like the phrase standard library. That is not really how this is going to be. That said, you do want common data structures for some things. So like we are going to make a math library with like stuff called vector3 and whatever, because if you don't have that, everybody has their own vector3, which again, if you want that, if you want your own vector3, that's totally fine. Party on, right? But when everybody has their own vector3, it's a pain in the ass, right? And so at least if people want to use a common vector3, they can. There's one there, right? But we don't want to do that for everything, just like some common stuff. They got bought out by Scopely. That has to be a joke. Do I plan on supporting BSDs before release? I don't know, man. We're busy right now. On Linux, do you see these systems calls directly? No, we use libc on Linux right now. Unfortunately, we have some compatibility problems due to that because we compile against Ubuntu right now, but we're gonna compile against muscle libc, which I had wanted to do years ago, but for some reason, somebody decided that wasn't appropriate or necessary, who I had assigned to do it, and so it didn't happen. And I just said, well, I guess maybe that person knows more than I do about this. And that did not turn out to be true because we did have compatibility problems before we even had 2 digits worth of beta testers. So I think if we do muscle libc and compile on Alpine Linux, then maybe that works, but I don't exactly know. How possible will it be to replace the vector3 lib you imported for your own vector3? So the plan is, the other way in which it's not a standard library is it doesn't work like C, where it's installed on your system, right? What happens is, I think this is the way Go does it too, but I don't have any Go experience. What happens is when you build a program, the modules that you were using for that program get copied into the source tree for your program, into a special subfolder, right? And thereafter, you use those. So, you maybe have some commands to update them or something if you want to update to the newest version, but for the most part, when you distribute your program, it comes with the source for all the dependencies, all right? So like if you wanted to use a different vector3, you just put it in there. Now you're going to have to, if libraries also wanted to use that same vector3, you need to make sure it's compatible enough that that works. But yeah, like if you don't like 10 lines in the middle of some function somewhere, just change it. And you don't have a problem with that because again, when somebody else compiles your program, they're not pulling their own system headers. There's no such thing as system headers. You've heard a handful of not small publishers using the indie fund term. Yeah, I know there was one that was called the indie fund. I remember that, and that was a cheap, stupid thing. And that was years ago, and I don't think that still exists. If there are more, I didn't hear of it, and I'm not that worried about it. I don't know, man. The new Go version modules thing does away with special vendor directory in your code. Instead, it uses a module cache folder somewhere in your system. That doesn't sound good to me. Wait, you're serious that Scopely bought Fox Games? That's crazy. Scopely is a company that we make fun of because someone Casey knows worked there, and it was bananas. Have I considered adding an explicit shadowing? Maybe. It's just not that important right now. Calling it indie fund style, yeah, that's fine. I mean, we pioneered a style of Recoup. If people want to adopt that, I'm okay with that. You can probably tell it to put the module cache in a subdirectory. Yeah, that's not the right way to do it. That's going backwards in my opinion. Like, you literally just want the program to have all the source with it that you need. And like, look, if that means that if you're building a whole Unix machine's worth of executables that you have way too much source, maybe you need to think about how many dependencies each program has and how many programs you have, and is that really necessary or useful or good? All right. But having a system module cache, I don't think is good. I mean, okay, the one case in which it maybe could work is if it was a read-only module cache, like nobody can go edit the files, and when you would copy it into the subfolder, you diff it against the module cache and make sure it's the same, and then just say that's a shared copy, right? But the problem is then you can't distribute your source to people. You can't just like copy the files because they won't have the thing in their module cache, right? And then you have to have or for people to get it, you have to have like a canonical repository with like version numbers that everybody agrees on, and then you have a lot of the same problems you have in the JavaScript world where like one of those becomes unavailable and now nobody can compile your thing. It's just not good. You don't want that. What was the idea behind C system libraries? Well, it's like, they just didn't think 30 years into the future when they did it, right? Which is fine. You can't predict that far ahead. Like in C, originally the C runtime was often very, very thin, and there wasn't much of a distinguishment between like, oh, this is basically a syscall and we're just marshalling the arguments versus, oh, this is like a more heavy runtime function. And then over time, the C runtime got heavier, right? But initially, like if a large percentage of the runtime is just operating system specific wrappers, then when you think about headers, you're like, yeah, those need to be different on every system, right? But that's not the way code is today. The way code is today, if you have a big library, the majority of the code should be the same on all systems if you can help it. And then you just have little exceptions about, not exception in programming language, but like little areas where you're customizing for like, oh, if we're on PowerPC, do it this way. If we're on ARM, do it this way, right? But those are minor parts of the code. And so you just don't want that to be different on different systems, right? You want the implementation to be the same. And then, but with those modifications. Anyway, we'll see how this plays out. Like, it could be that it doesn't work as well as I would like, but we'll find out. Let's go back to this Kozkov situation. So, we're going to do this. We're going to go. We're going to rename these to be a little less unwieldy. Okay. And then Syncof 5 is going to be similar, but different coefficients. Right. And then we can actually comment out the coefficients. It's interesting that it's actually not that much more code right now because, like, you get rid of the coefficients, right? Oh, wait, no. Hold on. Oh, right, these don't call eval1 ever. Okay. Okay. So hopefully that still works. It compiles. Oh, we got to change our thinger. I thought we did. I guess that was just the version in the game. This is libc. Libc. Okay, so we didn't appear to break anything. So let's do a release build and see. That should be like another 3% faster, roughly. Also, if you needed a thing to make you not need that code for each platform, you could use a library. That's not the standard library. Agreed. Yeah. The Golang module system works very well in the case you're not distributing your source code. Well, I don't know. I have no Go experience. I can't say. Okay. So we got slower again. I mean, that could just be vagaries of compiler optimization. I don't know, guys. I give up. We're back at original speed. In fact, we're a little bit worse, I think, almost. Okay, so what was Sean saying about breaking the serial dependency? He was saying, okay, let me just write down, what do we have here? We have A times X plus, okay. We have K0 times X plus K1, right? Times X plus K2 parens times X plus K3 parens X plus K4 parens X plus K5. Okay. So we're saying multiply it out, right? So I'm just going to do that. I'm going to just be super dumb and do it. K0 plus, or K0 X plus K1, close paren, X plus K2, close paren, X plus K3, close paren, X squared plus K4X plus K5. All right. I'm just going to do that again. I'm going to multiply the X squared through. Good thing I went to high school. K0X plus K1, close paren, X plus K2, close paren, X squared plus K, or no, X cubed, sorry, plus K3, X squared plus K4X plus K5. Oh, this is just, I see, this is just a very straightforward polynomial that they were factoring just to make something iterative. Like, that's almost obfuscating it. Like, it's clearer this way. Okay, but why get rid of libc? Because we need computers to be as simple as possible, both in terms of hardware and software, okay? And part of this language's goal is to give you a great deal of power over your code while simultaneously doing that as simply as we can. And what does simple mean? It means it's easy to do what you want, right? It means you don't get tangled up in operational snags like, oh, whoops, I need to link against this library, but that's built with debug and this one's release, or that one's built with the previous compiler and whatever, right? So that's why we have this model of compiling from source every time, of not binary linking against libraries, unless of course you're doing that, you know, because that's the job that you need to do. It doesn't happen incidentally. And part of that is just, things are very, very unergonomic these days in terms of amount of code that's being slung around, right? You have all these people with their millions and millions of lines of code. Most of it shouldn't be there, right? And so there's this mistaken idea that people have, that they get taught in school and also in industry, that like layers of code is good, right? Like, you have the code from the 70s, and then you make a layer on top that's from the 80s, and you make a layer on top that's from the 90s, and you make a layer on top that's from the 2000s, except it's like 20 layers instead of 5, right? And that's good, but it's not good, right? It's squishy, and it surprises you, and it causes problems. It's slow. I actually have a speech about this that I want to give soon that's going to be interesting. So you don't want all these layers underneath. You want to be close to the bottom, right? If you're going to build a new building, again, you dig a foundation for the building and build on that. You don't like smash down the previous building into rubble that's kind of flat and then try to build on that, because if you do that, your building is going to fall down in an earthquake. So that is the idea. The way the code was is a classical optimization to minimize the number of multiplies, right? Yeah, I mean, it's 5 multiplies. That's pretty good, right? Okay, let me see. K0x plus K1 x to the 4th plus K2x cubed plus K3x squared plus K4x. You know, there's something about polynomials that's nice. Like when I was learning them in high school, I was like, oh, so what? I kind of get it, but whatever. But like polynomials like this, and also like geometric algebra is just polynomials, but like in a slightly different way. It's just, you can get to cranking them around on paper, and it's really interesting. You get a lot done. I don't know. You should end up, compared to current code, rewrite each line as answer plus equals constant times x5. Oh, x to the 5th, answer plus equals constant times x to the 4th. Right. Yeah, that's what I'm getting here, right? So the equation is just, it just looks like a flat polynomial as opposed to like a recursive polynomial like this one is, right? So it's just k0 times x to the 5 plus k1 times x to the 4 plus k2 times x to the 3 plus k3 times x squared plus k2 x plus, or 1, 2, 3, I went backwards on k, k4x plus k5, yeah. I mean, it's just, there's x to every power times a constant. I totally get it. Okay, so what we're saying is, haha, we can't say xx because that's an operator right now. We're going to say x2 is x times x, right? And then x4 is x2 times x2. And then we're going to return. So this is k0. This times x4 times x plus this times x4 plus, and maybe there's a smarter way to do this. We'll look in a bit. It's going to force do this, plus this times x2 times x plus this times x2 plus this times x plus this, right? I mean, I guess the compiler can do a good job with that. You always found this easier to understand. Yeah, this looks very clear to me. Like when we were starting to do this, I was like, oh, that's uglier. But this is not ugly at all. This is just like, look, I understand what that means, right? No question. That is a polynomial. That is a 5th degree polynomial with some constants that were chosen to approximate something. Whereas this is like, I guess that's a polynomial. I don't know. It's worth grouping the times x4 multiplies to produce some of the multiplies. You just want some parallelism. Well, let me make sure I didn't screw this up, right? So let's, Still looks right. Okay. So we could group the x4s and the x2s and the x's, right? So we can go this is going to be a little harder to understand again, but like this this times x plus this times x4, right? That seems right. Right, and then this times x plus this times x2. And then if we're snotty, we can do that. These are actually all negative. Hey, look, you think this is the same polynomial? I mean, it probably is, right? S1, S2, S3. Well, they have more terms. They're doing this with 6 terms for some reason. We only have, oh, we do have 6 terms. One of them's constant. Duh. Why did I say 5? Okay. 1.6666666. 8.333. Yep. It's the same. I like this comment in the Sun version. Except they're saying degree 13, but this isn't degree 13. Is it? Is this somehow degree 13? Oh, because we pass ZZ. We're passing a squared variable in here. I remember that. Yeah. Okay. Well, we didn't break it. Let's see. Let's do that same thing here. I'm going to do it one step at a time again, right? Wait, this is K5? Or no, K0, K1. We can just do it straight up, right? So return whatever times x plus whatever times x4 plus whatever times x plus whatever times x2 plus whatever times x plus whatever. You know, all those people who said, when am I ever going to use these polynomials I'm learning in high school? They never made their own programming language. All right. It looks pretty reasonable. Maybe use x2 times x2 instead of x4 since you only use x4 once. It doesn't, that doesn't matter. I don't think. All right, watch it be slower. Ready? I called it. I called it. It is slower than the original version that iterates over the array. Maybe that's not the slow part, but it's actually getting slower. It's like, it's actually 10% slower now for some reason. I'm quitting computers. Most likely the slowdown is this one. No, listen to me. It is 10% slower just from the change that we did. That didn't come from elsewhere. That came from this code. And so it's still doing the same amount of work, but got 10% slower. That means the actual amount of intrinsic work involved in the job is probably many times 10%. So probably the slowdown is here. Although, I don't think Sean was here when we replaced sine and cosine with like messed up numbers just to do it. We could, hear me out, we could like do this and this, all right, just to see how much faster that gets. If we can run well enough. That's a pretty good approximation, right? That's pretty much a 13th order approximation to cosine of x. All right. Does anything appear on the screen is the question. Oh my God. Wait, what? Oh, because we're, well, he's getting bigger and smaller. Do you see that? He got big. I don't understand how the game is not more messed up than this. Let's see if we can move the camera. Oh, we can. How? Oh, wait. It's jumping around. It's jumping around. I honestly don't understand how the transformation matrices are mostly okay, though. How does it work at all? Okay, how did the tangent, how was the tangent function accurate to like 4 significant figures when I had the endianness of all the constants wrong. Calling the wrong code? I don't think so, because like this is definitely getting called because my viewpoint is snapping around. Okay, let's just see. What do we say for speed right now? Okay. It actually didn't get that much faster. It did get faster. It went from 8 to like 6.6. So maybe the answer that the slowdown is elsewhere is true. Like maybe all those if statements, maybe libc isn't doing those. Okay, let's try this for a minute. I mean, there's all this stuff, right? Outside of it, this is probably not that bad of an approximation to start with. You know what I mean? Like if we return a random number here, let's just return 0.5, okay? Sine and cosine, okay. If is sine, return 0.5, else return 0.8 minus 0.8. All right. This is going to be probably very messed up. Well, the guy is walking backwards. He is getting skinned on the GPU. But yeah, like I don't understand. Okay, I can't see anything in the editor. So that's interesting. Okay, that worked though. That was like a snap camera 2 thing, but I can't like rotate my view at all. It's just not moving. Okay. So I believe these are the right functions. We are actually calling these. I don't know what we're doing to build matrices. I guess for the character animations, we're multiplying together and then interpolating, neither of which requires sine or cosine. So that part makes sense, actually. Okay. Anyway. Like, we don't actually ever go... Like, to make a quaternion, you would call sine or cosine, but we don't go that direction usually. Except to turn guys, and that's why the guy wouldn't turn. But like, for entity like default poses, we actually save the quaternions on disk, right? So you start with the quaternion and generate the matrix from that, and that you do without sine or cosine. You just multiply terms around. Oh yeah, what was performance with that? Good question. Actually, I want to do this. I want to comment out all of this stuff. Because we don't divide by x, so we could even get rid of this, right? I want to comment out the boilerplate here, and we'll even make it incorrect. We'll get some casualties here. Actually, no, you know what? Let's go all the way. Let's say return, let's put it up here. If is sine, return 0.5, else return minus 0.8. So this is a pretty short sine or cosine function. And we're going to make a release build, and we're just going to see if that's not faster than libc, then it's got to be generating intrinsic instructions somehow, right? Like, I don't... All right. We're a lot faster than libc now. So it's all these if statements, actually. Well, I still can't turn. That's a problem. Maybe we're doing something that's crazy slow as well. You know, we could like move this halfway down the function kind of a thing. Let's put it there. Making release builds is going to be annoying, but you can eliminate some ifs using array indices, like when j is equal to 0 or 2. Yeah, but I would have thought that these ifs wouldn't be that slow, but maybe they're just poorly predicted. But these aren't. Like, well, this one isn't. All right. Shouldn't the compiler optimize it all out? Well, the static ifs, yes. I mean, the static ifs don't even get there, but I mean all the dynamic ifs. Okay. We are slower than libc here. Let's do this. We'll see if we can turn. Oh, guys, our is nan and is finite might suck. I bet that's it. I bet we're calling these and they're functions and they're shitty. Because we're doing those for every argument. Let's just try commenting those out and just running the rest of it. Shouldn't all the earlier code get discarded in an optimization build? We were returning. That's what it was right there. Return x or return 1 minus x. Maybe, but if it's calling into these and it doesn't know if they don't have side effects, then they would still happen. And if those are the slow part, I don't know. I'm just making up stories at this point. Maybe floor, maybe. All right. It's still slow. Maybe floor. I don't know. Like, we do call floor twice. Let's try this. Maybe it's doing a divide. All right, so we took out the floors. And I didn't declare identifier y. You're talking about different things, okay. Have you checked the generated code? The suspicion that I have is that I won't know how slow things are by looking at the generated code. We can do that for sure. I'm not going to know what actually takes time by looking at that. And the Intel tools for this are terrible, and I've never been, well, not never, but I haven't been able to use them productively in like a decade at least. Although Fabian does and says it's okay, but I don't know. All right. It's okay. So floor is very expensive is what we're seeing. We're probably calling libc floor. I don't know. Let's find out what our floor is. So like if we can make floor faster to just get down to this, then suddenly I feel a lot better about this being the default, right? You knew it was going to be argument reduction. I mean, maybe there's an overall more modern way to do this argument reduction, but let me just try a direct translation of this right now. Let's see, what are we doing for floor? Oh, it's a Cephes implementation in this very file. Yeah, that doesn't look cheap. We are doing this pointer thing. We could use a union to switch back and forth. Oh, we're calling is finite twice, by the way, because we already sort of like we know it's not zero. We know it's not zero, and we know it's finite. So we could skip that. That could be another compile time. Like we could do something a little crazy like skip checks is false, right? And if you pass true, we don't do these. But I don't know how much that's going to help. Maybe it would. What's is finite? I guess we commented that out and decided it wasn't that slow. Is nan is inf. I mean, you could certainly imagine this being faster. This is on doubles, yeah. Yep. I mean, I guess, okay, actually, well, okay. It is the case that we could get faster by doing a single precision version, but we're benching against libc's double precision version as well. For floats, you think there's a fast SSE float to int you can use as floor. Have you considered adding something like built-in expect is finite x comma true? What does that even mean? You can do the is finite check in the caller. Yeah, no, you can't, because this is for everybody to use. But my point was we actually already do that in the caller. So this, I mean, look. Basically, is finite just says, is this not equal to, like, okay, this is the following, right? Tell me if I'm wrong about this. Right? That's just simpler. Oh, except this is for float 64. And we need the float 64 version, not the float 32 version. So it's this, actually. Okay. Right? Can you change the floor with Libc's one? Maybe. Yeah. Well, nobody's saying this isn't right. So that's just UF and mask. Wait, what? You mean UF XOR mask? No. I mean, we could do it without the shift by leaving the number big, right? But then you have to load big constants into registers and stuff. Yeah. And then do we have an is finite for float? All right. Just make sure we run. We didn't use semicolons every day. Right. Uh-oh. This is bad news. I can't see anything. I'm screwed up. Wait, did I leave the sine and cosine? Uh-oh. Hold your horses. Uh-oh, guys, we haven't checked in a while. Oh no. Did I leave it? Oh, we took out the floors, right? Duh. We took out the floors. I forgot. Let's put the floors back for a minute. I was panicking for a minute there. Okay. floor is lava. Hey, I can look around. Okay. So we're going to go back to this. And we're going to find that this doesn't help much. Or maybe a little. Time to look at the disassembly of the libc sign. Yeah, that's not a bad idea. It's bedtime for me soon, so that may just be something that I do in the future. It's tomorrow already, everybody. Oh. All right. So, yeah, I would classify that as not helping noticeably. But, you know, these things add up sometimes. All right, so that's what our is finite is. Is nan is just calling this. But it's doing a bunch of extra work, right? This is actually biased exponent and not unbiased exponent. So why did I name it that? It's an unbiased corrected exponent. Anyway, like we're doing extra work to tell us if it's nan. Okay. An unbiased exponent, yeah. No, so I think floor is the problem. Let's try this. Like, is this going to help? Do we have any other checks we can do? Like, I sort of feel like this shouldn't be tremendously slow. So here's a question for people. I tend to do this pointer thing here. Do you think this is making the compiler freak out because of UB? And I should do the union thing, and then it'll optimize better. Yeah, we'll call libc floor. But you know what I'm saying? All right. Let's turn this off for a minute. It's my compiler. Why am I asking you? Yeah, well, it's LLVM. I don't know what LLVM is going to do. I guess it's not C++, but like it could decide there's an aliasing problem here, right? Or something. I don't know. I don't know, man. Okay, so we're going to say there's going to be a floor. We're just going to do the 64-bit version. So we're going to say there's a libc floor. That's called floor. All right. So this is libc floor, libc floor. Are those the only floors? Yeah. Let's just make sure it runs. CRT. All right. We gotta. Unfortunately, we don't. Yeah. I've got to do a thing where you can say these symbols are module visible, and I don't do that. All right. Do we run? It depends on what LLVM's rules are. Does it assume all languages have C-style UB? I don't think it's allowed to do that, right? I'm not sure. However, it's certainly but programmed by people with the same mindset, right? So they may be like, look, we can't do any optimization when we see this. It's not UB semantically because we don't know the language, but we can't do anything. It might be doing that, for all I freaking know. The LLVM way is to use the LLVM instruction that does this without UB. Yeah, like we could use a bitcast intrinsic. That is for sure true. That might be the next thing to do, honestly. Like if this turns out to be the performance problem, bitcast intrinsic. All right. The guy's movement seems broken. I think that was just low frame rate. Like it seems fine now. Okay, we got 1/7 faster, which is non-trivial. Doesn't solve all our problems, but so like, okay. Let's try, I don't know. Like at some point we do have to start looking at assembly to figure out what's going on. Will I make my own backend? We have our own backend already. It's just it doesn't optimize. It really doesn't optimize. Aren't I doing the same thing casting in my sign implementation? I don't understand the question. You wish you could just optimize math functions all day. It is kind of fun. Like, honestly, this is way more fun than figuring out why whatever Windows API call is returning invalid parameter with no further information. That's one of my least favorite things in the universe. I'm sure that happens a lot in Unix too. This is good. It's just I kind of want to know why this is slow, but you know, the good thing is when you have a problem like this, Like we win these, right? It's like the streamers say when they're playing a battle royale, like we win these. Like we're smart people who can make code go fast, right? So when we have a problem, we eventually just solve the problem. Sometimes it's by doing something unexpected and not doing things the old way or whatever, but we win these. So we're not winning them yet. We're not winning this one yet. Muscle does the argument reduction in a very different way, but it's like 10 times as much code. Why perf did not change much when you changed floor with libc's one? Oh, it did change. It got 1 millisecond faster out of 7 milliseconds. That's substantial. It's just, it just means floor isn't the whole problem. Like, I feel like we are getting bitten. Like, I feel like everything in here is slow for some reason. Which maybe means it gave up trying to optimize or something. I don't know why it would do that. But that could be what happened. It could just be that these branches all predict very poorly. I mean, well, we are picking a function that goes around a circle, right? Several times. So J is going to change for sure. What aspect of game development do I wish more smart people were working on? I wish more smart people were working on making computers simpler and easy to deal with and less buggy and less frustrating and less slow and less full of bullshit that you have to do in order just to get your program to compile. Muscles quadrant handling is elsewhere, but here's the remainder. So they just have a lot of cases. Are they just, they're doing the approximation with less terms by breaking it into more cases maybe? I mean, this is a lot more code, right? I mean, they're casting between int and float and stuff. That's a lot of code, yeah. There's an instruction for is whatever stuff. Yeah. So that's the thing is like, maybe we just make intrinsics for this stuff anyway. That'll help. Let me write down the ideas. So, is whatever intrinsics. What else did we say? Bitcast intrinsic. Like, I would just be interested, obviously I'm not going to compile muscle libc on Windows and compare, not obviously, but I just don't want to do that. But I wonder what the speed is actually. Like it might be faster, it might not. think you're returning NaN for both NaN and infinity inputs. So you presumably can combine those. Yeah, let's see. We return NaN here. We return NaN here. Although we return the same NaN. Like, does somebody care about that? Probably not. You're supposed to preserve NaN payload? Are you kidding me? Okay, but you could at least do one if, right? You could do the outer if to detect probably both of these cases. Because that's just, is the exponent, right? Is the exponent 7FF or whatever? And then inside you could say, okay, is the mantissa non-zero or whatever we said it was, then return that otherwise. So we can get rid of an if here for common cases. Right? Does that sound? I'm pretty much done for the night, but I think we just wake up and attack this tomorrow morning. So maybe we do that first. And then that informs what intrinsics we need. Oh, we could do this now, right? Let's make a, we kind of want, this, like, is NaN or inf is inline. Oh, this is the float 32 version, bro. So we want is NaN or inf. So we take this, we take the exponent, all right? And once we're in here, we say return true, right? We're going to copy this for later reference, right? Otherwise, return false, right? So we're just saying return this, right? Which means, of course, let's not bother wrapping that into a function. Let's just say exponent. Okay. And then we could just do this, right? Like, well, okay, let's just do this. Let's just do it all the way. If raw mantissa is equal to 0, that's infinity, right? Wait. Can we just not return infinity if it was infinity? Like, is that really bad for some reason? I think I can still use plain isNaN and isFinite. Yeah, I know. It's just, once you start breaking it down like this, well, we can do this for the purposes of testing to see if it helped at all, right? So let's not do this. We can do that if we want. It's just more code to understand for no benefit. Maybe. I mean, what if the compiler decides to inline that and then it pollutes the instruction cache and whatever, right? I don't know. I don't know, man. Also don't need, is it right? Because it's one or the other, right? So like that. I mean, that's not bad. Do you have any rule when you stop polishing a game? I stop polishing a game when I feel like it's no great detriment to ship it as it is. I feel like the important parts. It got slower again, everybody. Oh wait, no, because we turned the we turned floor back. So it's the same speed. That didn't matter at all. The exponent shift is unnecessary. Yeah, it's just like I'm just worried about big constants. Like this, you could load a small constant and like fixed shifts are fast, whereas loading an 8-byte constant is a pain in the ass, right? I mean, maybe it's fine, but so I think we got to at least look at instructions tomorrow to see what the hell this looks like. Because if it was just everything was equally slow, like if it was just like, look, these are not these branches. Well, okay, I guess this branch that we got rid of is never taken anyway, so it's predicted, right? So like, okay, we got rid of it, who cares? It doesn't matter. This one also probably doesn't matter. This one probably matters. And these probably matter. So if we're saying, oh, and this one probably matters. So if we're saying some of these branches are slow, it's those ones. Maybe the shift isn't that bad. The abs if is easy to optimize with an abs opt. Where are we doing abs? 7-minute abs, where is it? We're not calling abs. You mean this one? The problem is we can only optimize that for cosine because we need this, right? Or maybe there's something we can do. If x is less, yeah, this one. Isn't floor also doing a finite or nan check? Yes, but we just established that that didn't matter. So optimizing out another one also isn't going to matter. In theory. If is sine equals x right shift 63. And then you do the, right, you do the x XOR equals x right shift 63. plus or minus, right? Are we testing on x86 or 64? This is all 64-bit only. 64-bit instructions only. We do not support 32-bit CPU. You never use -1, for anything but a Boolean. Real? Okay, wait. That is true. Sine is essentially just a Boolean. We never multiply with it. Okay, let's do some hacker's delight here right before I go to bed. So we're going to say see if we can remember how to do this. We're going to say mask equals x right shift 63. Oh, you have to convert it to int, dude. That's going to suck. Let's try it. Oh no, we have it already. We need it to be signed, though. Oh, wait, no. Haha. I'm sneezing all of a sudden. I must have coronavirus. I think... I don't remember. Maybe we only force logical. Maybe you can't force arithmetic from... Let me see. This has happened to me a few times around midnight. I wonder if my building like turns on something bad and I get a stuffy nose. All right. So if this is signed, right, we can still do this just fine. Okay. And then if it's signed, then mask equals SF, right, shift 63. Right? And then X equals X XOR mask minus mask, right? So to negate a 2's complement number, you invert all the bits and add 1. Or, to leave it the same, you don't invert all the bits and add 0. So adding 1 is the same as subtracting -1 if all the bits are set. So you either toggle all the bits, add 1, or don't toggle all the bits, add 0. So branch-free way of doing this. And then this, if is signed, sign equals -1, we just say, I mean, I don't know, like, we could say sign is 0 or -1. I mean, we could just say sign times equals mask for now. I mean, that's kind of stupid adding an integer multiply, but... Oh, we could say sign or equals mask, all right? So if it's 1, it stays 1. Or if the mask is 0, it stays 1. Otherwise, it becomes -1. My xmath is bitwise mask on a double. I see your point. That is not going to work. I mean, we can do, I feel like this pointer thing is going to be slow if we do it, right? Like, I feel like this is going to hose us, but let's do it anyway. sign or equals mask. Oh, God. You're just making x positive, which just means clearing the high bit. If x is us, oh, right. So we don't even need an if there. Yes. Right. I'm doing a, okay. So what we're saying is this thing that I did here, this is wrong. This is a negation of an integer. All right. So this is what happens to me after midnight. It's like feeding the gremlins, right? This is negating an integer. We don't want to negate an integer. We want to negate the float representation. All right. And so all we want to do to the float representation is, I mean, the problem is we want this to be signed and unsigned. Or to do an arithmetic shift. Like, this is obnoxious. So I don't have a way to do arithmetic shift on an unsigned variable. So we either have to do signed or unsigned or do both here. And I don't know if doing both is going to slow us down. Yeah, we know it's the same as x and 7f. Yeah, we cleared that up. The problem is then I guess I can do that with the signed thing though. All right, so we could do that. The problem is, what do I do with sign now? How do I get that? I could say, I don't want to do an if, right? So I can do this, right? So before we AND it, do that. Okay, something like that, man. Presumably can do FABs. Yeah, but like we're literally calling into C or something. All right, so it functions maybe? Like those are matching. Except they're not. We're getting minuses. We're getting a 50 DKP minus here. This is not happening correctly. I don't understand why this doesn't do the same thing. This function was so beautiful 3 hours ago. It's not unbeautiful. Y sign starts as 1. I mean, yeah, we could do something different. I'm just trying to make it work the way it was. We can change what sign is later. And in fact, It's probably better to do that because then you could like if without comparing it. But for the purposes of just getting this to work, I don't understand why this doesn't work. I mean, okay, hold on. Like we can just simplify that, right? And let's just say pointer is this. So we get the thing out and we put it back in. Oh. Wait, what? Oh. I just did the wrong thing. Okay, so this assert is not going off. So then, oh wait, before we do X, there, still doesn't care. So right? Okay, it only happens in cosine, which is also weird. So this is, oh God, guys, I got rid of the if. I got rid of the static if. Thank you for telling me that 15 minutes ago while I was staring at this. Okay. 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 So if is sine. Okay. So this is still looks like an if, but it's a compile time if, so it should be okay. God, where did I go to programming school? And oh. This is like, it's just getting really confused parsing wise. I don't understand why it's getting confused, but like what is happening now? Okay, that was weird. All right. So there's some kind of parsing problem. That's going on the to-do as well. This. Okay. List is getting longer. Compiler uses different instructions for FFs depending on the register the value happens to be in. Great. That makes me so happy. The pointer right should also be in is sign. That's true. This is, like I said, it's the don't feed the gremlins after midnight. I'm actually very hungry, coincidentally speaking. Um, Wait, what? No. No, Sean. No. Because you want to absolute value X no matter what. I probably already had compiled that, but and that's how GNU libc code became what it is now. People optimized a lot. Yes, that is true, but there is such a thing as making the right trade-off where you don't uglify things too much for speed gains that are too debatable, you know. Yeah, the pointer stuff, I don't think the pointer stuff is good. So like, I think I tried tomorrow doing the union thing. It's the same speed, except it's occasionally spiking up. Well, now it's very noisy. Like, what? Why is it noisy now? It was pretty stable before. Oh, it's down. It's down. It's up. It's down. I mean, I feel like it got a little faster, but like, I don't know if this noise is due to something we did or if it's just like OBS is using more CPU now. That happens sometimes. But I do feel like it got faster, which would imply that branch free is the way to go with this function if we can do it. Intrinsics would be better. Yeah, like a float absolute value intrinsic, but honestly, I looked at how does Visual Studio do float absolute value? It stores it in memory and masks it and reads it. Like, seriously. Does SC2 not have abs? I don't think so. Fabs can be done with a single instruction on any register. Maybe the cast operator has some issue. Maybe. Like, yeah, like I was saying, I do think we want to look at the code. Copy negate max. Ugh, that's ugly, but it's probably faster than doing the pointer thing. I was remembering it wrong. It's not that Visual Studio writes it out to memory. It's just that it has literally an 8-byte constant that is all 0 except for the sign bit stored in memory, and it XORs with that or something, or, and not, or, it has a not of that. I don't know. You know what I'm saying? Come on. Yeah. I seem to remember doing something with big float constants like that. I don't remember what it is. Well, I'm just searching for and PS and DS and SS, and it's giving me CNS towing and auto service. S&S Brothers. Google is so good. I'll use these instructions. Intel Developer Zone. Okay, so what we're saying is like, look, we can do an intrinsic for absolute value. That still doesn't get us that far. We need one for floor, honestly. Like floor bought us a millisecond, remember that? So that would be my first choice. I love how these are all called MM, because that's the prefix they started when it was like MMX. Does always truncate towards 0 regardless of rounding mode. Hacker's Delight has something for floor. It definitely does. The question is, can't I just do something better? Floor replacement did not get much benefit. I think it did. Why don't I use Linux for programming? Because I need my computer to work. Unfortunately, Windows is getting worse at working every month, but it's still better than Linux for the time being. Omitting floor entirely was huge benefit. Oh, right. Yeah. Which just sort of, I tried like 17 of them. Dude, why do people ask me this stuff? Guys, I've been using Linux. My first Linux machine was 1992, probably. My first Linux machine is older than a lot of people in this chat. So like, don't give me this which distros have you tried stuff. It was 7-ish when you changed floor with libc. Okay. Okay, guys, I have the solution. The solution is that I license the Unity game engine, and then I go on the Unity Asset Store, and I download fast sine and cosine .cs. That sounds like the plan to me. You need fast ATN2 as well. Okay, so what are we saying? We could use intrinsics for isnan in isinf. Could use a bitcast. The bitcast, honestly, I do feel like the pointer thing may well be getting in the way in a serious manner. And so bitcast, except we don't need the bitcast really. If we have an isnan or inf intrinsic, then we don't need to do this. Right. Let's just like, you know, this wasn't good enough to leave it that way. And this wasn't good enough to leave it that way either. Although if this wasn't intrinsic, it would be fine. Somebody pointed out we know input is non-negative. So convert SD to SI converts 64-bit double to integer. Oh, you mean for the floor part? But only 32-bit integer. And you know, some of this stuff, like, look, floor here, like, if you really want to party down on this, like, multiplying by 1/16 and then taking the floor is the same as, like, having a floor 16 function, right? Because we multiply it by 16. So, like, if you just made, like, a floor 16 function, that's what you actually want here. And 16 is a power of 2. I don't know. It seems like this part, everything from here to, well, you know what I'm saying. There's a legacy SSE instruction that produces 64-bit output. Only with one specific encoding of the instruction. That sounds scary. Legacy encoding is just a type of encoding, nothing scary. Well, it sounds scary. All right, everybody. It is 1 a.m. It's time for me to sign off. I am not sure. So tomorrow morning, I either have to revert this or get it a little more into shape. I think I'm just going to leave it being a little bit slow for now and write a comment that says, hey, we got to speed this up, like with some intrinsics or something. But I'm going to leave it the default for a little bit. And we at least, okay, bookmark this. All right. We have a very definite path to getting off libc for math stuff, which is great, honestly. It's not great that it's slower than libc, but it is great that we can do this. I feel good about that part. And so then if we have some intrinsics here and whatever, that should help. I honestly don't know. Like, I'm curious if we get a floor intrinsic and one for this at a negate intrinsic or an absolute value. I mean, I don't know. Maybe it speeds it up a lot. I still don't feel like it's going to be 3 times faster. But again, I don't know how much damage this pointer thing is doing. It could be substantial. But I also, like, I wonder, this whole thing that it's doing about octants and making a number for octants, there might just be a better way to do that, right? Right? Like all of this, what are the chances you can't do that in less code? Like all of that is just put it in octants, set some signs based on which one. And, you know, at least look at the assembly. Yeah, we'll do that tomorrow. That looks simpler. Yeah. Yeah. This is one of these things where, like, you know, I was really enjoying playing with this function, right? And we did some good improvements on it. Like, it would be fun for me to just chill out for a week and, like, learn everything about this, like, understand the polynomial approximation very well, understand all this stuff very well, and then come up with something different for it. It's just, I've got so much that I need to do that I almost can't afford to spend a lot of time on this, you know? But I just need to get a summer intern who can somehow do this stuff. So getting rid of this code would be nice and just replacing it with intrinsics. Of course, it then goes internal to the compiler, but, like, you know. Anyway, this is pretty good. Like, you know, we did atan and sine and cosine today, and so, you know, it's maybe a couple more days to do all of these. And then we're just off libc for math. And then we can get rid of this horrible thing, which I don't even want to talk about. It's another cause of incompatibility. Did I think about opening up a little bit more for beta people? I mean, we're going to increase the size of the beta again at some point. Not yet, because one of the things I'm behind on is putting out the next compiler beta to people who are waiting for bug fixes and stuff. So I need to get on that. So that's maybe what I really should do with part of tomorrow instead of this. Maybe I should just push pause on this whole situation and just, we've resolved that we can do this and get accurate math. We know that it's a little slow. I could be thinking about how to solve that in the background, and then I just go work on compiler bugs, right? Like we got a couple of error message bugs today, and there are people waiting on other bugs. So, like, there's stuff I need to do here for sure. Anyway. Thank you, everybody, for coming by. I'm going to sign off. Is the game playable with slower sine cosine? Yes. You don't really notice the difference in the game. The only reason you see that it's slower is because we're doing a 400,000. Is that how many we decided to do? So we can do 400,000 of our slow sine cosines in 7 milliseconds. Approximately. All right. Thanks, everybody. I'll see you later.